Real simple. Let's start off by taking a look at the atom. You know, the atom is the smallest bit of any element. If you start cutting an element down smaller and smaller, the smallest thing that you end up with that still retains the property of that element is the atom. And there are a couple of different parts to the atom, different pieces to the atom. In the center of the atom, there's something called the nucleus, N-U-C-L-E-U-S, the nucleus. And then in orbit around the atom, there's this teeny-weeny little thing, a little subatomic particle called an electron. The electron is like a planet that's in orbit around the sun, basically. But the orbit's a little bit different. You know how in the sun, we have or in the solar system, the sun is in the middle, and the planets orbit around it in kind of a planar orbit. That is, they're all in what we call the plane of the ecliptic. They're all in like one orbital plane like this. The atom, the electron is kind of a frenzied orbit. The electron orbit moves all around the centrally located nucleus, all around like this, kind of like if you've ever taken the cover off of a golf ball, you see the rubber bands that are wrapped around it, or the old ones used to be anyway, or a softball, it's the string all wrapped around. If you could somehow see that electron orbit, that's what it would look like. It would kind of look like a very thin shell surrounding the nucleus. In fact, that's what they call the orbit of the electron. The orbit of the electron is called the electron shell, if you could somehow see it, which we can't really do. Now, we know that in the solar system, there's this thing called gravity, and gravity is what keeps the planets in orbit around the sun, right? Well, in the atom, there's a slightly different type of force that keeps the electron in orbit around the nucleus. But it's not called gravity. In the atom, this force is called an electrostatic force. And this electrostatic force is what keeps the electron in orbit around the nucleus. It's like an attraction between the orbiting electron and the nucleus. Kind of like gravity, works in a completely different way, actually. And I'm not a physicist, so I can't really tell you exactly how it works. Doesn't help you to fix games to know that anyway. What I just want you to see is that the electron exists here. Now, what actually keeps the electron in orbit around the nucleus is that the nucleus has what we call a positive charge. The nucleus has a positive charge. And the electron that's in orbit around it has the opposite charge. The electron has a negative charge. And there's an attraction between the positively charged nucleus and the negatively charged electron. It's just like with magnets. You know that if you take a couple of magnets and you put the north pole of one magnet next to the south pole of another magnet, they attract each other like this. Same thing with electricity. Opposite charges attract each other. And in fact, that happens to be one of the laws that we use in electronics. It happens to be called, and you don't really have to know this, it happens to be called the first law of electrostatics. The first law of electrostatics states that opposite charges attract. Opposites attract. Opposite charges attract. And again, it's just like it is with magnets. Opposite poles of a magnet attract, north pole and south pole. Opposite electrical charges attract as well. Yo, glad you could make it, Mel. Sorry. Mo. You could be Mo, but you're not. Where are you going to sit? You're going to sit right here, buddy. So opposites attract just like opposite magnets attract. So for instance, if I try to put a negatively charged electron next to something that's positively charged, those guys are going to attract each other. Now, just the opposite is true. If I try to put two of the same pole together, they'll repel each other. If I try to put two north poles together or two south poles of a magnet, they will repel each other. Same thing with electricity. If I try to put, let's say, two negative charges next to each other, instead of attracting, they'll repel each other. Same thing, if I try to put two positive charges together, they will repel each other. They won't attract. And we'll talk more about this as we go through the class. In fact, everything I'm going over now is going to be amplified as we go through the rest of the class. But what I want you to see here, the most important thing is these electrons. These tiny little electrons, these little subatomic particles with a negative charge. We can do things with these electrons. There's all kinds of things we can do with electrons, and this is what we're going to be dealing with this whole week. For instance, if I connect a battery and a lamp, the battery is like a pump for electrons. Instead of pumping water, it pumps electrons. And the electrons come out of the battery, they go through this wire, and the electrons go through the very thin filament in the lamp. The thing that's glowing inside the lamp is tungsten. It's incredibly thin. As billions and billions of electrons try to rush through this very thin filament of the lamp, friction causes it to get hot. It's friction, just like when you rub your hands together and your hands get hot. It's the same thing here. What causes the lamp to glow is friction between these electrons, these tiny little subatomic particles, and the very skinny little filament in the lamp. Causes friction, and it's the friction that causes the lamp to glow. We can do other things with these things, with electrons. For instance, we'll see later on that in the monitor, there's this thing called an electron gun, and I'll show you this closely later on. The electron gun, as the name implies, shoots out a stream of these electrons. That's what makes something glow on the front of the screen. What makes the picture is electrons shooting out of an electron gun, hitting the front of the screen and making light on the front of the screen. We can run electrons through a speaker and make the speaker make sound. We can shoot electrons at the light bulbs, at the fluorescent lights, and make the fluorescent lights glow. There's just millions of things that we can do with electrons. So this is what we're going to be going over this whole week. When we talk about electronics, what we're talking about is these tiny little subatomic particles, these little electrons. Everybody with me so far? The most important thing is that you realize that these electrons are not imaginary things. They're real physical particles. I think of electrons as like little BBs, basically, little negatively charged grape shot, or little tiny BBs. I mean, they're really itty-bitty, but they are real physical things. Now, when we have a setup like this with a battery and a lamp, this is called a circuit, an electronic circuit. And we can show what the circuit looks like in the form of a schematic diagram. If you turn in your blue book, if you look in your blue book, actually the blue book is set up in a couple of different sections. The front of the blue book is all the text, and then right in the middle of it there starts the reference section. And all the parts in the reference section start with the letter R, R1, R2, R3, and so on. The schematic symbols are on page R1 and R2. The schematic symbols are supposed to kind of represent what the part is or what it does. And the schematic symbol for a battery looks like this. Long line, a short line, a long line, a short line like this. And the long line is the positive side of the battery. Now, any multi-cell battery is drawn like this. And in this case, this 6-volt battery here, there's actually 4 individual cells inside this battery, 4 individual cells. If I were to draw the schematic diagram or the schematic symbol for a single cell, like a flashlight, like a D cell and a flashlight, it would just look like this. But any battery that's more than 1.5 volts will be shown like this. To show you what the voltage is of the battery, it will generally be labeled off to one side like this. In this case, it's a 6-volt battery. So that's the schematic symbol for the battery. The schematic symbol for the lamp looks like that. It looks a lot like a lamp. The circle is the glass envelope of the lamp, and the little curly Q inside is the filament. And then, of course, connecting the two together, we have these wires here. And the schematic symbol for a wire is extremely complex. Just a line like that. And when we have all this stuff hooked up, we have what is known as a circuit. C-I-R-C-U-I-T. Or in Spanish, circuito. As I just got back from Mexico City. So I'm still thinking like Spanish. Okay, now, in order to have a circuit, you really have to have 4 things going for you. This is pretty important. In order to have a circuit, and this is actually technically called a complete circuit, you really need to have 4 things. Number 1, you have to have what we call the source. The source of power. Remember I mentioned that a battery is like a pump. Is like a pump for electrons. Instead of pumping water, it pumps electrons. Obviously, if we're going to get electrons to move through a circuit, something has to be pushing them through the circuit. You have to have some, just like water, you need a pump to pump water through a circuit. Electricity is the same way. You need to have something, some source of power, and in this case, the source of power is this battery. The source of power could be like the AC wall receptacle. The source of power could be a power supply, like this one is, power supply from a game. Whatever the power source could be, a windmill or anything. Anything that's providing the push for the electrons is called the source. Then you need to have something that's using the power from the source. If I just have a battery like this with nothing else connected to it, this is not a circuit. This is just the source. In order to have a complete circuit, you have to have something that's going to use the power from the source. And we call that the load. The load is anything that's going to use the power from the source. The load, in this case, is a light bulb. But in a video game or a pinball machine, the load is like the logic board. Or in a pinball, also the load would be the coils. There's another load that's the coils. And it's a whole separate circuit, actually. So you need to have a source, and you need to have a load. But you need 2 other things as well. You need to have a way to get the power from the source to the load. You need to have some kind of a conductor, some kind of a wire, some kind of a piece of metal, something that's going to conduct the electricity. And we call that the source path. The source path, the path that the electricity is going to follow as it goes from the source to the load, is called the source path. But you wouldn't expect anything to light up with just one wire hooked up. I mean, obviously, if I have my battery here, I connect the positive lead to the battery, goes to the light bulb, but I don't have anything hooked up, obviously the light bulb's not going to be on. So you need not only a way to get the power from the source to the load, in this case the light bulb, but you also have to have a way to bring the electric current back from the load back to the source to get the thing to light up. So we need not only the source path, but we also need the path that brings the electric current back from the load to the source. This is very important. This is known as the return path. We're going to talk a lot about source path and return path as we go through the class. And when we have all of these things, when you have the source, the load, the source path, and the return path, you have what we call a complete circuit. In order to have a complete circuit, you need to have all these things working for you. I mean, obviously, you wouldn't expect this thing to light up if there was just one wire hooked up. And all these things are a complete circuit. According to the schematic diagram, according to the way the schematic diagrams are drawn, electric current flows from positive to negative on the schematic diagrams. The way the schematics are drawn, electric current flows from positive to negative. Huh? Wait a minute now. I just got finished saying that electricity is these electrons, and these electrons are little, get over here, are little negatively charged things. If electricity is these little negatively charged electrons, and opposite charges attract each other, electricity really should be going from negative to positive, shouldn't it? When you think about it, I mean, that's what an electron is. And yet, according to the schematic diagram, electric current flows from positive to negative. Well, there's a reason why. And the reason why is that it's only in the beginning of the 20th century, I should say, that we discovered what electricity really is, that we discovered what the electron is and all that jazz. But they've been drawing schematics for hundreds of years. I mean, even Benjamin Franklin did a lot of experimenting with electricity. You know, the kite flying experiment where he flew the kite in a storm and, you know, lightning hit the kite and he touched the key at the end of the kite wire and shot the shit out of himself. Oh, lightning's electricity. Hey, no shit, Ben. You know, but he did a lot of experimenting with electricity. Get over here. I'm not sure why it's doing that, actually. I think the fluorescent lights are messing it up. Anyway, it's got a mind of its own. Yeah, hi, how are you? Okay. Anyway, Ben did a lot of experimenting with electricity, and he also drew schematic diagrams. Well, what they thought electricity was in the beginning was some kind of weird invisible fluid. They thought that electricity was some mysterious invisible fluid, and they thought that some things had too much of this invisible fluid, and they called those things positive. And they thought that some other things didn't have enough of this weird invisible fluid, and they called those things negative. And they said electricity flows from positive to negative, and so they started drawing schematic diagrams that way. Well, when we discovered hundreds of years later that electricity is really these negatively charged electrons, they did not change the way they draw schematic diagrams. Schematic diagrams are still drawn kind of bass-backwards. Schematic diagrams are drawn as if electricity was some kind of invisible fluid and it flowed from positive to negative. Now this concept of electricity flowing from positive to negative is known as conventional current. Conventional current. It ain't really the way the electric current flows, but it's the way we draw the schematic diagrams. And so throughout this class, almost without exception, when we're discussing electric current flow and we're discussing how things work in schematic diagrams and so on, we'll be talking about electric current in terms of conventional current, this concept that electricity flows from positive to negative. Now, it really doesn't. Electric current really flows from negative to positive. But since all the schematics are drawn this way, this is the way we need to look at it. Also, it makes it much easier to understand how electricity works, because when you look at electric current as flowing from positive to negative, it works the same way that water does. Everybody knows water flows from a higher altitude to a lower altitude. Same thing with electric current. It flows from a higher voltage to a lower voltage, and we'll talk a bunch about that as we go through the class. I guarantee you this is really very simple. So as far as we're concerned, when you look at electric current flows from positive to negative. It would come out the positive side of the battery, through the load, that's the source path, and then the return path is back to the negative side of the battery. Does that make sense? And as long as we have these four things we have a complete circuit. The source path, the load, the return path, we have a complete circuit. If something happens and the circuit is broken somewhere, let's say the source path has a break in it, we no longer have a complete circuit. If the source path is broken, this is now known as an open circuit. An open circuit. And in an open circuit, there is no flow of electric current. Obviously, if I break this connection somewhere, I'm not going to get any light to light up. You know, complete circuit, obviously. If I break the connection somewhere, like break the source path here, open circuit, no current flows. If any current was flowing, obviously the light bulb would light up. Well, if I break the source path, I have an open circuit. But if I break the return path, don't I have the exact same thing? When you think about it, if I break the return path, the light bulb still ain't going to light up. And back to that old thing, nothing lights up with just one wire hooked up. So it doesn't matter where I break the current flow. If I break the source path, no current flow. If I break the return path, no matter where I break it, I can break it down here at the battery, no matter where I break it, the light bulb goes off. Okay? So if we have an open circuit, there is no current flow whatsoever. This is just the opposite of a short circuit. For instance, if I connect like a metal blade, like let's just take this knife blade for instance, across the terminals of the battery. I'm just putting it right across the terminals of the battery. The light bulb goes off. I'm going to hold it up so you can see it. Why? Well, obviously it's much easier for the electrons to go through this nice thick knife blade than it is for them to try to squeeze through the really skinny filament of the lamp. The electrons will take the path of least resistance, I guess you would say. When I have this, what the hell was that? Oh. I thought something was blowing up on me. And I knew I had unplugged Vigilante, so I couldn't figure out what the hell it was. If something happens and I end up with a direct path right across a source like this, this is not an open circuit anymore. This is now a short circuit. And in a short circuit, generally you have excessive current flow. That's usually what blows fuses when you have some kind of a short circuit. So we can have a complete circuit, normal, everyday, everything's working hunky-dory, complete circuit. If the path is broken somewhere, we have an open circuit, no current flows. Or if we have a direct path right across the source, we have a short circuit. The reason I point this out is that a lot of people just automatically assume that any failure that they have is a short circuit. Like they equate short circuit with bad, like they mean the same thing. Like you go to a location and they'll be pointing to the pinball and they'll go, hey, that number 5 bonus light doesn't light up, it must have a short in it. Well, bullshit, it's probably open, isn't it? The filament of the lamp is probably broken, it probably has an open circuit. So don't think that any failure is a short circuit. Some components, when they fail, do short circuit. I'll show you that diodes, there's a part called a diode we'll look at, for instance, that always short circuits. When it fails, it's always a dead short. It's very easy to find. Transistors sometimes short, sometimes they open circuit. Resistors, we'll look at a part called a resistor shortly, it always open circuits. That's all it ever does when it fails. So we're going to look at both these types of failures, short circuits and open circuits. Just remember that in a short circuit you have excess current flow. There is nothing stopping the flow of electric current. With an open circuit, if you have a break in the wire somewhere or a break in the component, no electric current goes through at all. That's an open. Everybody with me so far? Okay? Pretty simple, right? But a lot of people make that mistake. They say anything that's bad is shorted, and that's not necessarily true. Well, before we go too much further then, let's take a look at some of these terms that we use in electronics. And a lot of the terms that we use in electronics are kind of weird because they're named after people. They're named after early pioneers in electronics and stuff like that. In fact, they're named after dead guys, basically. So let's learn some of these dead guy terms. And one of the first terms that we want to cover is the term voltage. Voltage is our electrical term for pressure, our electrical measurement for pressure. Now, if I was talking about water pressure, what's our unit of water pressure? Yeah, PSI, pounds per square inch, right? Sure, PSI. Voltage, our unit is the volt. Voltage is measured in volts. 1 volt, 2 or more volts, pretty simple. In this case, named after a guy named Alessandro Volta. He's an Italian guy, and he's the guy that invented the battery, like hundreds of years ago, invented the chemical battery. And so we measure voltage or pressure in volts. For instance, that 6-volt battery, this has, whoa, hey, oh, hey.
The fluorescent lights.
That's it, fluorescent lights. Have a nice trip. See you next fall. Okay, this is a 6-volt battery. It has 6 volts of electrical pressure. And since this is a 6-volt lamp, I'm all discombobulated now. Since this is a 6-volt lamp, it glows pretty normally because it's got a 6-volt battery attached to it. Your car battery, on the other hand, is probably 12 volts. It has twice as much pressure. If I were to connect this 6-volt lamp to the 12-volt car battery, it would glow like really incredibly bright for a short time, and then it would burn out, obviously. So the higher the voltage is, the more pressure you have. The power from the AC wall receptacle down here is 120 volts. Yeah, Claude. This is 120 volts coming out of the wall receptacle, 10 times what comes out of your car battery, 10 times the pressure. On the other hand, all of the games that we use, all of the integrated circuits, or almost every integrated circuit in every game you work on, requires 5 volts DC to operate. Most of you are probably familiar with this because your power supply has a 5-volt output, and this is very critical. We'll talk more about this. We'll talk a lot about this, in fact, because this has to be very exact. The 5 volts DC can only vary plus or minus a quarter of a volt before we start to see problems. That's one of the reasons. In fact, it's almost the main reason, not really though, why you want to have a digital multimeter so that you can check it accurately, because that 5 volts really has to be accurate. We'll talk a lot about that as we go through the class. You can imagine what would happen if you ran 120 volts of pressure into the 5-volt logic board. I mean, the extra pressure literally blows the tops off of all the ICs on the board. It's really, you know how I know that? Because it happened to me once. It was really a disaster. Just bam, just craters all the chips. And of course, that makes troubleshooting easy, doesn't it? You just replace everything, and that's it. It's a terrible, horrible thing to have happen. In fact, we'll talk more about this. There's a type of a transformer that you'll use in every game called an isolation transformer. It's a safety transformer. And without this isolation transformer, there's a possibility of putting 120 volts on your logic board. This is like a real common problem in Mexico, apparently. They go, well, I don't need no stinking transformer, and they don't put it on there and blow stuff up. So
this thing is nothing more than a converter.
Well, we'll talk about it in great detail coming up. It's an isolator. It isolates everything from the AC power line. I'll give you the straight poop as we go through this thing. I'm just trying to introduce you to some different terms now. So one of the things that we use our meter for is to measure voltage. And it's probably what most of you are, the only thing you're using your meter for right now is to check the 5-volt power supply maybe, or to see if you have AC power coming from the wall receptacle. But there's lots of other things that you can use the meter for, as you'll see later on. So voltage measured in volts, that's one of the things that our meter will measure. The next term is current. And current is defined as the flow of electricity. Just like current in a river is the flow of water in a river, so too the flow of electrons, or actually, since we're talking about conventional current, let's just call it the flow of electricity, is called current. And our unit of current is the ampere, A-M-P-E-R-E. It's another dead guy. In this case, the guy's name is Andre Ampere, one of your countrymen, Claude. And I don't really know what the hell he did, to be honest with you. He's some kind of electronic genius. I don't know. But current is measured in amperes, but nobody says amperes. Everybody just says amps for short. Amps, A-M-P. 1 amp, 2 or more amps. If you say amperes, people look at you like you're really strange. So current is measured in amps. Current is the flow of electricity in a circuit. How much actual flow is there in a circuit? Now, although the meter can measure amperes, we never actually measure amps. We never actually have to do it when we're working on games. There's never any reason whatsoever, as far as diagnostic tool is concerned, for us to ever measure current when we're working on games. So we never have to do it. In fact, the only time that I've ever even measured electric current in a game is just out of curiosity to see how much electric current a game maybe draws from the wall receptacle, or how much electric current a logic board might draw from a power supply. And by the way, your average video game only draws about 1.5 amps to 2 amps out of the AC power receptacle. This is especially important for those of you that work in arcades or setting up arcades. How many games can you put on one circuit breaker? Well, if you have a 20 amp breaker, obviously, if you put 10 on there, you'll be fine, 10 or less. So, what do you guys have, like a mess of them loaded up on a circuit breaker or something in your place?
No, we got 2 geared up with 220.
220s, 220 amp breakers. Oh, okay. Not 220 volts. Okay. Scare me there. Go, 220, what? What are you doing? So, okay. Yeah, fire sale, yeah, really. Well, this happened to me a couple of times. I worked in England for about a year, and when people would send us, when we get equipment like from the United States, a lot of it came wired from 110, and we had to be very, very careful that we didn't plug it right into the wall, blow it up. Anyway, so voltage we will measure with our meter. Current we don't have to measure with the meter. And then there's one other term we want to look at, resistance. Resistance is defined as the opposition to the flow. The opposition to the flow of electric current. Now that's, that's really complicated. Here's what I really mean by that, though. Imagine that I'm out in my backyard and I'm watering my garden out. I'm watering my petunias out there or something. And of course, the amount of water that comes out of the end of the hose is determined by the spigot over here, the pressure at the spigot. You turn on the spigot or the faucet or whatever you want to call it, and the water comes out. If someone comes along and kinks the hose, it's harder for the water to get through that kink, right? That's a resistance. That's slowing the water down. What happens to the amount of water coming out the end of the hose? It trickles a lot less, right? So the more resistance you have, the less current you have flowing in a circuit. Everything has a certain amount of resistance. For instance... come back over here. For instance, thank you. Obviously, the filament in this lamp has a certain amount of resistance. It's harder for the electrons to get through the skinny little filament of the lamp than it is through the wires. So the lamp must have some resistance. Now, the wires aren't glowing like this. The wires aren't glowing because they're thick enough that they can handle the amount of current that's going through them. But of course, if I tried to jump start my car with these little clip leads, they probably would look like that, wouldn't they? Because the starter motor in a car draws hundreds of amps of current, and it would just fry them just completely. So now theoretically a wire has no resistance, a theoretical wire, but we know of course that they must have resistance. That's why you use thick wires for some things and thinner for others, because you need to draw more current, let's say, for the starter in a car. And we'll see later on when we take a look at conversion kits and how to hook up games that to carry the 5 volts from the power supply to the logic board, you want to use several wires. You want to use 3 or 4 wires, because they'll have less resistance that way, and it will enable the electric current to flow much more easily. So resistance is defined as anything that opposes the flow of electric current in a circuit, and resistance is measured in ohms. OHM, 1 ohm, 2 or more ohms. In this case, named after a guy named George Simon Ohm. And I don't know what he did either. But this is another one of these dead guy terms. I guess eventually we'll have the Elvis, but I'm not sure what that's going to be. So anyway, and resistance is another thing that we'll measure with the meter. We have a symbol that we use for ohms, and that is this symbol right here. It's the Greek letter omega. The little Greek letter omega. See the little Greek letter omega there on your meter? And that indicates that this is the place for ohms. This is where you set your meter for ohms. Right there. So we will measure voltage with our meter. And there's volts. This is called volts DC, volts AC, which we'll talk about the difference in just a minute here. And we will use our meter to measure volts. We will not use the meter to measure current, to measure amps at all. We're never going to use that amp setting, even though it's there, and we could do it, we're not going to ever do it. And then this is where the meter would be set for ohms. Failed miserably. Let's go back to that. Let's go back to this circuit that we looked at previously with the battery and the lamp, this complete circuit. And remember I said that electric current flows from positive to negative. In this circuit, our source of power, our source is DC. It is direct current, yeah. The definition of direct current is current that flows only in one direction, only from positive to negative. A battery is a pure source of direct current. In the battery, the electric current flows only in one direction. It comes out this red lead, through the red wire, through the lamp, back down. The return path is through the black lead, back to the battery again, only in one direction. Direct current. Let's replace the DC source with an AC source. And an AC source would generally just be indicated with a circle and this little squiggle in the middle like this. And we're going to talk a lot more about this little squiggle. This little squiggle means alternating current. It happens to be called a sine wave, but I'll tell you more about that later on, so don't worry about it for now. But this would be alternating current, or AC. And the difference between AC and DC is that alternating current is constantly changing direction. Alternating current goes in one direction for a short time, and then it goes back in the other direction. Alternating current is constantly changing direction. It's constantly changing polarity. First it goes this way, and in this case our AC power coming out of the wall is 60 cycles per second. So it goes this way for 120th of a second, then it goes back for 120th of a second. That's one cycle. We'll talk a lot about this later on. Goes this way for a short time, 120th of a second, and then it comes back again. So the difference between DC and AC is that DC, the current flows only in one direction. In AC, first that side's positive and that side's negative, and the current flows this way. Then the polarity reverses, and the current flows the opposite direction. That's the difference between AC and DC. When we're making voltage tests, as we'll do, not quite often, as we'll do occasionally. Actually, I'm going to show you many ways to test things without the power on at all, which is really the preferable way to test things safely, no shocks, power off. But when we check things like direct current, and you're checking voltage with your meter does have two leads. It has a red lead and it has a black lead. The black lead goes into a jack marked common, C-O-M for common. We have a reference point that we use when we're making DC measurements, and it's called ground. It's called ground. Ground is our 0 volt point. When we're making DC voltage measurements, we almost always put the black meter lead on ground. In fact, there's many cases I'll show you where we'll put the black meter lead on ground. And in fact, I'll even show you one where we'll put the red meter lead on ground, but that's a kind of an interesting and unique test. But whenever we're making voltage checks, we'll almost always put the black lead on ground. Ground is our 0 volt reference point. It's just like, let's say we're talking about a pilot, and the pilot's flying around and he calls his altitude into an air traffic controller. He doesn't give his altitude above the earth, does he? Because that's always changing. He'll go over a mountain or whatever. What does he use? Well, he uses sea level, right? Sea level, right. Or sea level is, like ground is our electronic sea level, basically. And we have a couple of different schematic symbols that we'll use, several actually, that we'll use for ground. One of them, and the most common one that you'll see, looks like this. Kind of forms like an arrow that always points down to the bottom of the schematic diagram. This is called an earth ground. It's called an earth ground because when you see this ground symbol, it is somewhere, anything electrically connected to this symbol is somewhere actually electrically connected to the earth itself. You know that if you look at our AC power distribution, it looks like this. And there's a short slot and a longer slot, and then this half round guy, and this is an earth ground. Somewhere in the building, this third round pin is supposed to be connected to like a cold water pipe that's buried in the ground, or perhaps a steel rod that's pounded into the ground somewhere. The earth itself is our 0 volt reference point. And so that's the earth ground. And of course it's 0 volts. In fact, the long slot is also 0 volts. It's called the neutral, N-E-U-T-R-A-L. It's called the neutral side. That's also 0 volts. Theoretically, I should be able to stand with wet feet on wet concrete and stick my tongue in that long slot and not get a shock off of it. On the other hand, the short slot is what we call the hot side, and that's the side that has the 120 volts AC on it. Whenever you set a new, location or a new street location or a new arcade, it's really a good idea to check the AC power to make sure that it's properly grounded and everything's hooked up right. When you check from the hot side to neutral, you should get 120 volts AC there. When you check from the hot side to ground, you should also get 120 volts AC. If you check from the hot side to ground and you get something like 40 or 50 or 60 volts AC, you have no ground at all. It's floating. The ground is floating. This can be dangerous because you no longer have a safety ground, and sometimes the effect will be you'll touch two rails of two different pinballs and you'll get a shock, or even just touch the control panel of a game if you're wearing if you're wearing no shoes, I should say, if you're wearing bare feet, and you might also get a shock. Also, when the game's not grounded, all kinds of weird electrical impulses can get into the game. It can blow logic boards. It can blow power supplies. This is a real problem in Mexico. Real bad problem down there, and ain't nothing grounded properly in Mexico. Nothing. And so you can get shocks off all kinds of weird stuff. Here in the United States, it's not really so much of a problem. Anyway, so earth ground is 0 volts, and it's actually connected to the earth itself. You will see me draw a kind of a shorthand version of this same earth ground symbol. I'll often draw it like this because it's a lot faster. These two mean the exact same thing. They mean this is exactly the same as this. It always points down to the bottom of the page. Earth ground. Well, you know how in most vehicles you have a 12-volt car battery, and you know how the negative side of the car battery is connected right to the chassis of the car? It's called negative ground. If you lift the hood of any car and look at the car battery, the negative side of the car battery will be connected through a real thick wire, and it'll go right to like the engine block or the chassis or something like that. It's what they call a negative ground system. But in your car, the car is up on 4 rubber tires. That ground cannot be an earth ground. There's no possible way. It's not touching the earth at all. So we have a separate kind of a ground. It's called a chassis ground. Chassis ground. And the chassis ground is a different symbol. It looks like this. It is still 0 volts. It's still 0 volts, but it's 0 volts. It's not connected to the actual earth itself. And when we start looking at the monitor schematics, you'll see that the ground symbols are all chassis ground symbols for reasons which I'll explain later on when we start looking at monitors. So either of these things are 0 volts. Okay? Any questions so far? Okay, now one more thing before we take a break. Let's go back to our car here, automobile. Here's the 12-volt car battery. The negative side is connected to the chassis ground. There's the positive side, 12-volt battery. Goes out here, and let's say it goes to my radio or something. There's the DC power going into the radio. That's the source path, isn't it, right? The path from the source to the load, which in this case is my radio. My source is the battery, load is the radio. Well, remember, I need to have a return path for a complete circuit, and the return path is back to ground like this. Can everybody see that by putting a ground symbol here and a ground symbol here, it's electrically exactly the same thing as if I were to draw a wire in between the two? I mean, ground is simply just the metal part of the car chassis. It's a big, giant, fat wire, obviously. So that's pretty obvious, but this is actually an important concept. Ground is the same everywhere. When I draw ground in 2 or maybe even more different places, like, for instance, it not only goes to the radio, but there's also, I've got a CB rig, right? That side of that would also be grounded, right? That's the return path. The current flows into the radio, but current also flows into the CB. The return is back through ground. There's lots and lots of things in anything, in a video game, a monitor, a pinball, whatever. There's lots of things that are connected to ground. And instead of having a wire going back to a central ground, which would be really complicated and the schematic diagram would be a mess, instead, they put a ground symbol everywhere that it goes to ground. But everybody can see that these are all connected together, correct? All right. In order to make circuits work, they do have to have, certain parts of the circuits have to have a certain amount of resistance. And to get that certain amount of resistance, we have these parts called resistors. And that's the parts that I've given to you, and I'll be giving you some more as we go through this later on. Turn in your handbook, in your big blue book of really swell technical information, to page R3, I think it is. The schematic symbol for a resistor looks like this, just a zigzaggy line like that. In games, we use resistors with a very wide range. In games, we have resistors that are as little as 1/10 of an ohm. And we also have resistors that are 1 million ohms, or even more than that. So we have a very wide range of resistances. In fact, there's one monitor that we use. It happens to be the monitor that's in the Vigilante game there, and also this one under the table, that has a 2.2 million ohm resistor. But the size of the resistor has nothing to do with how many ohms it is. Now, I've handed out some resistors to you, and hopefully you have different resistors, but these resistors can be any number of different ohms, and yet they're all the same size. If you look at these teeny-weeny little resistors here, first thing you'll notice is that there are no numbers printed anywhere on this resistor. In order to tell what the value of the resistor is, we have this thing called the resistor color code. The resistor color code. And it's real important that you know the resistor color code. You don't necessarily have to memorize it, but you just do have to know the resistor color code, and the color code is there on page R2 and also on page R3. Each color represents a number. For instance, 0 is represented by black. Get a different pen here. 1 is brown. 2 is red. These are in ascending chromatic scale. That is, they're the same way a rainbow is set up, if you know how that works. 3 is orange. 4 is yellow. 5 is green. 6 is blue. 7 is violet. 8 is gray. And 9 is white. Now, if you look carefully at your resistor, you'll see that there are actually 4 bands on it. Now, it may be extremely difficult for you to see those bands. These resistors are pretty damn tiny. And it may also, for the men in this room, it may be difficult for you to tell what some of the colors are, because men have a problem with color blindness that women don't. So you can ask Shirley or Susan when we get later on into this thing what colors your resistors are. But if you look carefully at your resistor, you will see that one of the bands is gold. One of the bands at one end is gold. We're going to start talking about the resistor at the other end. We're going to start talking about the resistor at the end opposite the gold band. So let's take a look. Let's say we have a resistor that is, let's say, blue is the first band, and green is the second, and red is the third band. Forget about the fourth band for the moment, the gold band. We'll start with the other side. Well, how many ohms is this? Let's see. The first band is blue, so that's 6. So we'll write down the number 6. The second one is green. Green is 5. Write down the number 5. And the third band is red. That's 2. This is not a 652 ohm resistor. Okay? This is really important. In a resistor, the third band of the resistor is technically called the multiplier band. It's called the multiplier band. Ooh, what the hell does that mean? Well, all it really means is that this third band tells you the number of zeros to put after the first 2 digits. In other words, it's telling you to multiply times 10, add 1 0. 100, add 2 zeros. Multiply by 1,000, add 3 zeros, and so on. Blue, green, red. Blue is 6, green is 5. The red, the third band, is telling me how many zeros to put after the first two. How many should I put there? 2 zeros. This is a 6,500 ohm, and there's that Greek letter omega. This is a 6,500 ohm resistor. Okay? We don't know what a K is. This is a 6,500 ohm resistor. The third band has to be the multiplier because, remember I said that we have resistors that are 1,000,000 ohms or so. If the third band was not the multiplier, if you just wrote down the number it was, what would be the largest value in ohms you could have with 3 bands? 999 ohms. Yeah, 999 ohms. So unless you want to have a resistor that's this long just so you can put all the zeros in there, somehow you have to do it a different way. And so this is the way we do it. The third band is the multiplier band. We're going to go through a bunch of these things, and then we're going to do a little resistor lab in just a second so that we'll have a good idea of how this works, because it's real important to know the color code. All right, let's say that we have a resistor like this one. Let's see, grab another color here. Let's say we have a resistor that is, I only have 4 colors, so we're going to have to fake this. Let's say we have a resistor that's green, red, orange. Beautiful orange, all right. All right, green is 5, red, orange, 3. 523 ohms, right? No, Randy, you dumb shit. What is it? It's three zeros, right? 1, 2, 3, 52,000 ohms. Okay, let's do a couple more. Let me just instead of trying to find the color here, let's say we have one that is let's say we have one that's yellow, violet, yellow. Yellow, 4, violet, yellow, 4 more zeros, right? 1, 2, 3, 4, 470,000 ohms. Don't try to do this in your head, because it's very easy to slip up and lose a zero or something somewhere. For instance, you might have a resistor like this that's brown, black, yellow. Instead of trying to do this in your head, look at it and say to yourself, okay, brown is 1, black is 0, yellow is 4. 4 zeros, 1, 2, 3, 4, and then put the comma in and see what the hell you have. Because it's very easy to drop a 0 or add 1 accidentally, especially when you get into something with a large number of zeros. So don't agonize over it. Just write it down. Just write down whatever it happens to be. Let's say we have one like this. Let's say we have one that's red, violet. Let's go nuts. Red, violet, green. All right. What's red? 2. Violet. 7. Green. 5 more zeros. 1, 2, 3, 4, 5. See, 2,700,000 ohms, right? So it is actually very simple once you've done it a few times, and we're going to have a chance to do a bunch of them here. All right, now put on your thinking caps. How about this one? Suppose we have one that is brown, black, black. Brown, black, black. What do you suppose brown, black, black is? What do you think? 1 ohm? Anybody think anything else? 100 ohms? Anybody think anything else? Point what? What was that, Dan? 10 ohms? All right, how many think it's 1 ohm? How many think it's 10 ohms? How many think it's 100 ohms? Who thinks it's 10? Okay, 10 ohms is correct. 10 ohms is correct. Let's see why. This is a tricky thing, but there's a reason why I point this out to you. Okay, brown is 1. We got that. That's easy. Black is 0. Okay, the third band is telling you the number of zeros to put after the first 2. How many? Zeros. Don't put no freaking zeros back there. It's black. This is a 10 ohm resistor. If that third band is black, it's saying don't put no zeros back there, none whatsoever. You do put the second one in there. That's normal. That's a significant digit, as they would say. But the multiplier says don't put any zeros back there. Here's why this is important. You need to pay attention. This is very important. Let's say that you were working on something, and for some reason you found this resistor. I'll get it. Fine, just fine. All right, let's say you're working on something and you see this resistor. Resistors, by the way, are the last thing that you test. Resistors hardly ever fail. I'm covering them first, but they hardly ever fail. But let's say for some reason you're working on something and you see this resistor and it's brown, black, black, and you think to yourself it's 100 ohms. Most people think it's 100 because they go 100 and they think it's 100 ohms. I'm really surprised that so many of you thought it was 1. And they get to the thing, they see this resistor, and for some reason they want to check it. So they put their meter on ohms. This we'll do in just a little bit. They put their meter leads across the resistor, and the meter doesn't read 100 ohms. It only reads 10 ohms, which is what it really is, right? They go, oh, I'm a genius. I found it. This resistor's partially shorted. It's supposed to be 100 ohms. It's only 10 ohms. So you boogie over to Radio Shack, and you get a 100 ohm resistor to put in there. You may not notice that the colors are different. You know, it'd be brown, black, brown, wouldn't it? If it was 100 ohms, it'd be brown, black, brown. So you may not notice that the colors are different. You go ahead and replace that 10 ohm resistor with the 100 ohm resistor. Obviously, when you turn the thing back on, it doesn't fix anything, does it? Because you not only changed a good part, but you've changed one with a part that's the wrong value, right? You made it worse because even if you eventually find which part is actually bad, you may never get it to work because this new resistor you put in there is 10 times the value it should be. So here's why I point this out to you, and this is really important. It has to do with the way things fail. When a resistor fails, it always open circuits. It goes way up in resistance. When a resistor fails, it never goes down in resistance. In fact, the only time you would ever see a resistor that was lower is if you look at the board and it's just a little chunk of carbon or charcoal sitting on the board, obviously all flamed out, in which case you'd find it by looking at it, wouldn't you? Visual inspection, by the way, is critically important. It's really important to look at jazz. I find about half my problems just by looking at them. That's why if you're in a dark location, it's really important that you have a good trouble light. You know, this business of you got the pen light flashlight in your mouth like this and you're trying to work on something like this and you know, that's nonsense. You really have to have a good strong light to be able to see what you're doing. But again, when resistors fail, they always go way up in resistance or infinite resistance. So like let's say you have a resistor that's supposed to be 470 ohms, let's say, and it's bad. It will be open. You'll put your meter leads across it. Your meter will read an infinite resistance. And we're going to do a resistor lab in just a few minutes here so you can see what I'm talking about. You will never, ever see a shorted resistor. Never look for one. It will always go way up in resistance. So, does that make sense so far about the color code? Now, they do have these little gadgets that you can get at Radio Shack, these little thumb wheels that you can rotate to line up the colors, and it tells you what the value of the resistor is. It's really hardly necessary. It's important that you remember the color code, though, and there's a few little jingles that you can use to remember the color code. These are... The first letter of each word of the jingle is the first letter of the color. For instance, there's 3 that I know of. There's a really clean one that I learned in Boy Scouts. That's better be ready or your great big venture goes west. Better be ready or your great big venture goes west. That's kind of queer. That's kind of stupid. But... if you're the drinking type, I got a good one for you. Bad beer rots our young guts, but vodka goes well. That's a good one. Bad beer rots our young guts, but vodka goes well. But the one most people remember is bad boys... Okay, Howard, settle down. Bad boys rape our young girls, but Violet gives willingly. I suppose in today's climate of awareness, that's probably not such a good one. But bad boys rape our young girls, but Violet gives willingly. So if you remember those, that's the first letter of the color code anyway. Anyway, and if you want to remember it in Spanish, it's negro, café, rojo, naranja, amarillo, verde, azul, violeta, gris, and blanco. Correct? All right. Pretty cool. Huh? I learned that in Mexico City last time. So rico suave. All right. All right. So anyway. Now, remember I said that we use some very large values for resistors in the thousands and the millions. And so we have a kind of a shortcut that we use when we're talking about large values. Something called a metric prefix, which you probably already know what this is, even though you don't know that it's called this. For instance, we use the metric prefix kilo. Kilo, of course, means times 1,000. A kilometer is 1,000 meters. A kilogram is 1,000 grams. We have kilovolts. 1,000 volts is a kilovolt. And we also have kiloohms, K-I-L-O-H-M. 1 kiloohm is 1,000 ohms. Well, nobody says kiloohm. Everybody just says K for short. If you look at the meter, down here is the ohms department. Right there. For instance, when the meter is set on 200 ohms, we can read up to 200 ohms. With that setting, the meter will read up to 200 ohms, actually 199.9 ohms. If you set the meter on the K scale, you can read up to, in this case, up to 2,000 ohms. Whatever you read on the meter display up here will be in thousands of ohms. That's very important. If the meter is set on K, and the meter up here, the display says 1, it's actually 1,000. It's actually 1,000. If the meter is set on 20K, you can read up to 20,000 ohms. If the meter is set on 200K, you can read up to 2,000 ohms, and so on. Now, some meters are auto-ranging. For instance, on this meter, it doesn't say K on it. You just set it to ohms, and it automatically sets itself for the proper range. Some meters are like that. Some meters are not. I personally kind of prefer the meter where you actually set it to whatever range you want, because it makes you more aware of what's going on. On an auto-ranging meter, you have to be careful. You'll see a little K in the upper corner, usually, of the meter. Maybe it's real big. It depends on the meter you get. That tells you how many ohms it is. But my little K is a teeny weeny tiny little letter in the corner of this meter. If you're not careful, you may be reading 10 ohms. You may think you're reading 10 ohms, but it's really 10K, where you won't have that problem if you have the other type of meter. But some people prefer auto-ranging meters. It really doesn't make that much difference. So we use kilo as one of the metric prefixes we use. For instance, if I have a resistor that is, let's say, 2,700 ohms, 2,700 ohm resistor, this will be referred to as a 2.7K, right? 2.7K. Of course, you divide by 1,000, you just move the decimal place over 3, don't you? So that would be 2.7K. And if you look at the schematic diagram, the schematic symbol, or on a schematic diagram, you'll see the resistor here, and it will be labeled like R123, whatever the resistor number happens to be. It might say something like 2.7K. It might have the omega after it. Okay. We also have resistors that are in millions, and so we have another metric prefix, mega. Mega means times 1 million. For instance, a power generating station might be referred to as providing so many megawatts of power, millions of watts of power, megawatts, millions of watts of power. And we also have megohms, M-E-G-O-H-M. 1 megohm equals 1 million ohms, obviously. So, same thing, and if you look again at your meter, for those of you that have this type of meter, or something similar, you'll see that the two highest scales are megohms. There's a 2 megohm scale, right? And the next one up would be 20 megohms. You will probably find that you'll never use those ranges working on games. You'll probably never use those ranges when you're working on games. As we'll see in just a little bit, when you start doing this resistor lab, the proper setting for your meter, if you don't have an auto-ranging meter, is to be as low as you possibly can without getting some kind of an overload indication. Now, this particular meter says OL on it. It says OL. That's when the resistance is higher than what you have it set for down here. Other meters might just have the number 1 with no digits after it. You'll see when we start doing the resistor lab how simple it is, and we'll do that in just a few minutes. So, same thing with large value resistors. If I have a resistor that is, let's say, 1,200,000 ohms, that would be 1.2 M omega, 1.2 megohms. And that's the way it'll be on the schematic diagram. It'll just say 1.2 M omega like that. Make sense? Okay. Now, sometimes we have these itty-bitty resistors. We have these resistors that are in fractions of an ohm. For resistors that are 10 ohms or less, we have another way of denoting what the value is. Sorry, stand by. The first band of a resistor is never black. That is, it's never 0. You would think that if let's say we wanted to have a resistor that was 1 ohm, you would think that it would be like black, brown, black, wouldn't you? But it's not. The first, for some reason, I have no idea why. The first band is always brown or higher. That is, it's always 1 or more. But we have resistors that are fractions of an ohm, like maybe 2.7 ohms or a fraction of an ohm, like 0.27 ohms. We have another way of showing you this, which value is which. Say, for instance, I have a resistor that is red, blue, which would actually be 26, wouldn't it? 26. If the third band, remember the third band is the multiplier, right? If the third band is gold or silver, this is what we call a fractional multiplier. And this is how we get values that are less than 10 ohms. It's called a fractional multiplier. Now, remember I mentioned you have 4 bands on it, and your 4th band is gold on the resistor that I gave you. We're not talking about that band yet. I'm talking about the 3rd band. You probably don't have one of these in front of you. But if the 3rd band is gold or silver, here's what it means. If the 3rd band is gold, instead of like telling you to add zeros like the 3rd band usually does, it tells you to multiply times 0.1. If it's silver, it says multiply times 0.01. So let's say, for example, I have a resistor that's red, blue, gold. Well, red is 2, blue is 6. The gold says multiply times 0.1, which of course means just move the decimal 1 to the left. This would be a 2.6 ohm resistor. If the 3rd band is gold, bless you, if the 3rd band is gold, the fractional multiplier tells you to multiply times 0.1. If, on the other hand, this was red, blue, silver, silver says multiply times 0.01, which would be moving the decimal 2 to the left, it would be 0.26 ohms. The place that you commonly see these resistors is in these switching regulator power supplies, like these guys. There are some fractional multiplier resistors in here that you'll see when you open these things up on Wednesday. But that's how we get our values that are less than 10 ohms. The third band, instead of being a color telling you to add 1 0, 2 zeros, 3 zeros, or whatever, instead is gold or silver. So what the hell's that other colored band, that other metallic band? Well, the fourth band of the resistor is called the tolerance band. Remember, the third band is the multiplier. The fourth band of a resistor is technically called the tolerance band of the resistor, also known as the percentage band. Here's the deal. These resistors that I've given you are called carbon film resistors. And what they are inside is a little cylinder made out of ceramic. Just like, like a china plate, just ceramic. And deposited on this ceramic cylinder is a thin spiral of carbon. Now, carbon, of course, is one of the elements, and pure carbon actually conducts electricity pretty damn well, almost like a wire. But by making this carbon very, very thin, it has more resistance. Obviously, the thinner it is, the more resistance it will have. The way they change the value of the resistor, the way that same size resistor can be 10 ohms or 10 million ohms, is they make the spiral winding thinner. This makes more resistance because naturally the thinner it is, the more resistance it has. Plus, if I were to unwind it, the longer it would be, They got more spins on it. In fact, when you see on the rare occasion that you see a burned up resistor, if you brush it aside, you can see the burned up part. You can see the spirals wrapped around it. Anyway, then they clamp a metal lead on each end of it like this. And then they dip the whole thing in this epoxy, which is why it has a kind of characteristic dumbbell shape if you look at it, or dog bone shape. And the bigger ones, it's even more obvious than that. I'll show you one in just a little bit. So these are called carbon film resistors. Anyway, they cannot make these things exactly perfectly accurate. Every one is not exactly perfectly accurate. The fourth band tells you how accurate it is. If the fourth band is gold, as most of them are, as probably all, I would say almost all of them that you'll encounter will be, it's a 5% resistor, meaning that it could be plus or minus 5%. If it was 100 ohms with a gold band, it would be 95 to 105 ohms, somewhere in that range. And virtually all the ones that you'll see in games will be gold. If the fourth band is silver, it's a 10% resistor, meaning plus or minus 10%. You'll probably never see that, and you'll probably never see one of these either, although they do exist. A resistor that has no fourth band is 20% tolerance. I guess they figure if it's that bad, they're not going to bother putting a band on it at all, and they just don't. So this one's terrible. Let's not paint it. You'll never see that in games. But if you go to a surplus electronics store, you might see a resistor that has no fourth band on it. So just so you know what it is, that would be 20%. You wouldn't want to use that in games. Quite frankly, silver or gold, either of these would probably be perfectly acceptable in a game, certainly. Okay. So resistors actually have 3 different specifications. When you go to an electronics store to buy a resistor, you just can't say, hey man, I need a resistor. I need an R56. He's going to go, Yeah, there's 3 different things you have to tell him. Number 1, the resistance in ohms. How many ohms is that resistor? Is it a 1K resistor? Is it a 10K? Is it a 2.7K? Is it a 500 ohm? What is it? Number 2, the tolerance. Really, nobody calls it that. Everybody just calls it the percentage. And then there's one more specification. It's called the dissipation of the resistor, and it's measured in watts. The resistors that you have in front of you are 1/4 watt resistors. 1/4 watt. But we also use resistors that are larger than that. We use resistors that are a 1/2 watt, or 1 watt, or 2 watts, or 10 watts, or even higher. For example, this little resistor is the 1/4 watt size that I gave you. Where are we? Here's a 1/2 watt. Both of them are very common. We see both of them in game. 1/4 watt, 1/2 watt. You can see the size difference between the two. They also make larger ones than that. They make 1 watts, and they make 2 watts as well. Now, for larger than that, when we get to larger values than that, we use these kind of resistors. This is called a, what do you call it? It's funny, some people call it that, and I've only heard that a few times. This is technically called a ceramic wire wound resistor. But some people call them sand resistors or cement resistors or power resistors. But if you look at it, first of all, you see that it has the value printed right on it, doesn't it? You can see it says 0.47 ohms, 10%, 5 watts. Those are those 3 ratings. Number 1, 0.47 ohms, resistance in ohms. The wattage, the tolerance, 10%, and the dissipation in watts, 5 watts. These are called ceramic wire wound resistors. That's a 5 watt. Here's a 10 watt, 10 ohm, 10%. You see in the upper right hand corner right up here it says 10 watts. Also a ceramic wire wound resistor. Here's a 25 watt, 1 ohm, 25 watts. But these guys are called ceramic wire wound resistors. Ceramic wire wound. They're called ceramic resistors, obviously, because they're made out of ceramic. I mean, that's you can see obviously that they have a ceramic cover on them, and inside, instead of being made out of carbon, which can burn up, they're made out of wire, like in your toaster or your hair dryer, the stuff that's glowing inside there. Same kind of wire, basically, resistance wire. If I'm not mistaken, it's nichrome, a nickel chromium alloy. You don't really have to know that. But they put the resistor inside here and then seal it up with this ceramic, because these things get quite hot. It's not, you've encountered that, haven't you? It's not at all unusual for these things to be like hot, like really way freaking hot, way hot. They get really hot. In fact, here's a little shortcut you can use to test these things. When I see a big resistor like this, I'll just touch it. If it's hot, it's good, period. Why? Well, because when resistors fail, what do? They open circuit. If the resistor's open, ain't no current going to go through it. It ain't going to get hot, right? Actually, that's the way resistors work. The way resistors resist is they turn the current flowing through them into heat. Now, the teeny-weeny resistors won't get hot enough to feel, but although they do generate some heat. But I think you're all aware of there's this thing called conservation of energy that states that energy cannot be destroyed. It can only be changed from one form to another. Remember that? Star Trek 16 where Spock gets caught? Well, never mind. Anyway, so the current going through it gets changed into heat. So if I feel this thing and it's warm, it must be good. Now, I'm not saying that if it's cold, it's bad. Big difference between the two. I'm saying if it's warm, I know that it's good. If it's cold, maybe it is bad because maybe it's open, or maybe whatever the circuit is that's supposed to be sending the juice through it ain't working, something like that. But I know in a fraction of a second, if I can touch it and it's warm, it's good. In fact, as we go through this class, I'm going to show you dozens of common shortcuts like that. Real quick things that you can do to tell if something's good or bad. Very often you can just look at a game and infer what's wrong with it just by what it's doing. And we'll cover that anyway. So in games, we use a wide variety of different dissipations, different watt. Nobody calls it dissipation. Everybody just calls it the wattage of the resistor. You know, how many watts is the thing. And most of the time, there'll be quarters or halves, and you'll rarely be replacing these resistors because they just hardly ever fail at all. All right, so what we want to do now then is we're going to take a break, but at any time during this next half hour or so, here's what I want you to do. If you look at page R3 in your book here, what I have here are 12 resistors. This is pretty self-explanatory. I have 12 resistors here, and underneath the 12 resistors, I've got 12 lines. I want you to put down the value of each resistor. And for instance, if we look at the first one here, let's just do the first one. Red, violet, orange. Red is 2, violet is 7, orange is 3 zeros. This would be 27,000 ohm, or 27K is what I want you to put down. I want you to put it down in K. Now, naturally, any resistor where the third band is orange is K, isn't it? I mean, that's pretty easy. And what's the percentage? The tolerance? 5%, right. Now, we can't tell anything about the dissipation because they're just printed on the page, obviously. So I want you to do all 12 of those. And now on the next page, R4, you have a place for 5 resistors here. And I'm going to make sure that you get 5. I think you only have 3 or 4 now. Whatever. 3? You only have 3? Well, somebody's got 4. And I have 5 things down here, 5 lines. What I want you to put down is number 1 on the first line where it says band 1, band 2, band 3, band 4. I want you to look at your resistor, try to figure out what color it is. If you cannot figure out what color it is, as I often have trouble doing, sometimes you may have to simply measure the resistor, get an idea of what the value should be, and that'll tell you what the colors are probably. If not, ask Shirley or Susan, right? Yeah. What the colors are, because for sure they'll be able to tell us where we probably can't figure it out. Indicated resistance. What is the color code telling you the value should be? What is the color code saying? How many ohms should it be? Then I want you to measure it with your meter and see what the value actually is. When you measure the resistor with your meter, you should not put both hands on the meter leads, because your body resistance will affect the reading. In other words, if I put my meter leads across, let's say if I just put my hands on the meter leads, you could see the meters, well, maybe you can't see it, but the meter's doing something. It's freaking out because of my body resistance. So when I check a resistor, I can put one hand on the resistor, no problem. But my body's out of the circuit now, isn't it? If I'm just holding the meter lead, touch the other meter lead to the resistor, my meter says 0.996K, or about 1,000 K. So this is a 1 meg ohm resistor, really, is what it is. So presumably this is brown, black, green. What? Wait a minute. Which it isn't. Let me see what... Oh, 0.9K. I'm sorry. Almost 1K. It's a 1K. It's 0.9K. Sorry, I misread it. See what I mean about that little K up there? It kind of freaks me out. It's almost 1K. This should be a 1K, which it is because it's brown, black, red, which is a common resistor. So you can take a break now. I want you to go through all this. At 11:30, we want to go over what we've just done. Okay, let's go over these things on page R3, the 12 resistors. Resistor number 1, red, violet, orange, gold. We went over that one, 27K, 5%. Resistor number 2, orange, orange, orange. Sounds like Trix cereal, doesn't it? Orange, orange, orange. Obviously 33K. The silver means it's 10% in this case. Next one down, brown, black, red, very common resistor, 1K, 5% means it's gold. Number 4, violet, green, yellow, that has to be 750K, 5%. Number 5, gray, red, orange, is 82K, Gray is 8, red is 2, orange means it's K. 20%, right? No fourth band at all, so it's 20%. Next one, God help you if you got number 6 wrong. Brown, black, black, we talked about this one. That's our tricky 10 ohm resistor. Remember that guy? 10 ohms, 5%. Number 7, brown, red, green is 1,200,000 or 1.2 megohm, right? If you put 1200K, you are correct. It is 1200K. That isn't how you would order it, and that isn't how it would be on the schematic diagram. It would be 1.2 megohm. Number 8, stop me if you have any questions, by the way. Number 8, red, red, yellow, 220K, 5%. Number 9, white, brown, brown, 910 ohms, 10%. The silver is 10%. Number 10, yellow, violet, gold, gold. That's one of those fractional multipliers. Yellow, violet is 47. The gold says times 0.1, 4.7 ohms, 5%. I think you'll find that all your fractional multipliers will be 5%. Number 11, also fractional multiplier. Red, red, silver, gold. Red, red, 22. But the silver means times 0.01. So it's 0.22, isn't it? Number 11 is 0.22, 5%. Number 12 is also tricky like number 6. Brown, green, black is 15 ohms. If you put 150, you screwed up. Remember, the black band means no trailing zeros, no multiplier zeros, and 20%. Okay. Now the other page I can't really go over because everybody has different resistors, so I'm not going to go over that one. But we do see the same values over and over again for resistors. After a little while of working with resistors, you get pretty familiar with them, and I see the same values, the same common values over and over again. Here's what I mean. I can get this thing erased. For instance, you commonly see 10 ohm resistors, and you see 12 ohms, and you see 15s, and you see 22s, and you see 27s, and you see 33s, and you see 47s, 56s, 68s, 75s, 82s, and 91s. But you don't see all the values. In other words, they don't really make some of the values. There's some, like they make 18 and stuff. But I see powers of 10. In other words, I see 100 ohms is common, 120, 150, 220, 270, and so on. These are all common values. So are these, 1,000, 1,200, 1,500, 2,200. What's changing here? Just the third band, huh? The multiplier is the only thing that's changing here. So in other words, I see lots of brown, black, brown, red, brown, green, red, 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 violet, especially common. So is yellow, violet. Very common. I see orange, orange, and so on. I see these combinations, and then we just change the multiplier band. So for instance, I see a brown, black, red resistor. Well, that's really familiar to me. That's a 1K. We use those a lot. But you hardly ever see 2K resistors. You see 2,200 ohms, you see 2,700 ohms. You don't see the 2Ks. And the reason you don't is that, remember the tolerance, the plus and minus part of this whole deal. If you go up a little bit in tolerance this way and down a little bit in tolerance this way, right in the middle is kind of where they meet anyway. So you don't see every value under the sun. So it's pretty easy after a while. You look at a resistor. For instance, if somebody tells me that they've got a resistor that's 73 ohms or 730 ohms, I can say almost without a doubt, bullshit. You don't have that resistor because they don't make that resistor. How could you possibly have it? You know, if somebody says, I've got a resistor that's 5,000 ohms, bullshit. You might have a 4,700 ohm resistor, or 5,600, but you probably don't have a 5,000. They really just don't make. They make them, but they'd be like precision resistors that we just wouldn't use. So you see the same 1, 2, 3, 4, 5, the same maybe dozen first 2 color combinations over and over and over again, and the only thing that changes is the multiplier. Now, when you have a bad resistor, what you'll measure is an open circuit. Let's see if I can stop that right now. I put my meter on ohms. I have a resistor here that is supposed to be 2 ohms. It says 2 ohms on it. So you would expect it to be almost like a short circuit, basically. It's only 2 ohms of resistance. When I put my meter leads across the resistor, you see the meter does nothing. It does nothing at all. Oops. If I'm not touching it with my hands, that is. It's supposed to do nothing at all. That's why it's important to keep your hands off the meter leads. You see the meter says OL, open. Just as if I'm not touching anything at all. It's supposed to be 2 ohms. It says 2 ohms on it, but it's open. And it even says on the back of it, open. So always pull your resistors out. If they say open on the bottom, they're bad. This one also says open on the bottom. But obviously, I wrote that on there. This one, this is a humongous resistor. This is an 80-watt resistor, gigantic thing. 330 ohms, 80 watts. When I put my meter leads across it, nada, nothing. The meter shows me nothing. Well, it doesn't show me no ohms. It shows me infinite ohms. It doesn't change at all. Obviously, open resistor. So this is what resistors do when they fail, is they open circuit. Very often, very often we need to have a resistor that we can adjust, and that's what these things are. They're variable resistors. A variable resistor has a more technical term. A variable resistor is technically called a potentiometer. Oh my God, what a word. It's called a potentiometer. Yeah.
I don't want to interrupt you, but before you get on to the subject, is it okay to link a bunch of resistors together in series to make a different size?
There's Jeff's question. Okay, well, all right. Let me back up then and let's discuss that for a second. Sure. I try not to get into that too much because I at this beginning stage it's a little more complicated, not terribly so, but the question was asked by 2 people, so I'll answer it. If you take 2 resistors, and remember this is the schematic symbol for a resistor, and connect them like this, so that any current going through one part has to go through one part to get to the other part, this is known as connecting components in series, in a series circuit. We'll talk more about this later on. In any system, doesn't matter what it is, anytime you have to go through one part to get to another, they are in series. For instance, if we go back to our little circuit with the battery and the lamp, if I connect 2 lamps like this, these lamps are in series. They're in a series circuit because naturally all the current has to go through one lamp first before it gets to the other one. When you connect resistors in series, the resistance is added together. Let's call this R1 and R2. R1 plus R2 would equal the total resistance. In other words, let's say if this was a 1K and this was a 10K, so the math is easy, R sub T, the total resistance would be 11K. So for example, if for some reason, let's say you needed a 1K resistor, but you didn't have one, but you have 2 470 ohms, because they don't make 500s, right? You could take 2 470 ohm resistors, put them in series, that would be the equivalent of 940 ohms, pretty damn close. And for us, in our circuits that we use in games, probably close enough. That's called putting resistors in series. You simply add them together. On the other hand, does that make sense? And you can put 2 or 3 or 4 or 5 in series. Doesn't matter. You just keep adding them all up. That's fine. On the other hand, if you connect resistors like this, now the current doesn't have to go through one part to get to the other. The current appears across both at the same time, doesn't it? This is known as a parallel circuit, P-A-R-A-L-L-E-L. And in a parallel circuit, again, let's call this resistor number 1 and resistor number 2. If they are the same value, let's say they're both 1K, 1,000 ohms, the total resistance would be 500 ohms. It would cut it in half. If you put two resistors in parallel and they are the same value, your total resistance is exactly 1/2 of what each one is. If I put 3 resistors in parallel and they're all the same value, it's 1/3. In this case, it would be 333 ohms if they were all 1K. Now, if they are unequal and you're putting them in parallel, now you got a big deal going. Now we get into something called Ohm's law, and it's really an involved deal. If they're uneven, so I put a 1K in parallel with a 1500 ohm or something like that, it's R1 times R2 divided by R1 plus R2. Forget about that. Like I said, I'm not trying to make an engineer out of anybody. If you ain't got the right resistor, go to the freaking store and get a right resistor. You could do this. I've done this more than once. And I'll show you later on with something called a capacitor, where you really sometimes need to do this too. But quite honestly, since resistor failures are so rare, and a bag of resistor like this costs you a couple of dollars for a giant bag of resistors, even from Radio Shack, there's no reason why you shouldn't be able to come up with the correct value resistor, to be honest with you. But as far as simple work like that is concerned, putting them in series adds them up. Putting them in parallel, if you just always make a point of using the same value and put them in parallel. Now, if you're like me and more of a practical guy, because my mathematics suck, which is the reason why I'm not an engineer, because I could never do the math. If you want to make up a value of a resistor, you got a meter there. Just start putting them together until you come up with the right value. Measure, put them together, measure it. Oh, it's a little bit too much. Add a lower value resistor or whatever, and just keep measuring until you get the right value. But I seriously doubt that you'll ever have to do that. So anyway, does that answer your question?
Oh, yeah.
Okay, Dan, you cool? Or whoever asked that question? Oh, sorry. Oh, was it you, Hondo? Oh, it was you, Ken. Oh. See me after the class, but I can't carry you right now. All right, so anyway, let's go back to these variable resistors or potentiometer. They call potentiometers potential. The term potential is another fancy word for voltage. And a potentiometer they use to change voltages on things. Nobody calls it a potentiometer. Everybody just calls it a pot for short. So this is the only kind of pot you're allowed to have at NAMCO. And we use potentiometers all over the place. For instance, in the power supply, there's a voltage adjustment potentiometer right here that used to adjust the output voltage of the power supply. In a monitor, there's a mess of pots in the monitor. Things like adjusting the vertical hold of a monitor, the vertical size, horizontal hold, just about anything that you twist to adjust. A volume control on a board is the potentiometer. Pots, they're all the same thing. I have a little pot here that I've hooked up just to give you this really fabulous demonstration here. I've got a potentiometer connected to a lamp. As I adjust the pot, the lamp dims. Ooh, ooh, yeah, that's good for 15 seconds of fun. All right. Okay, so anyway. Let's just take a close look at the pot, and you'll see what I'm talking about here. And if we look here at the pot, and you can really kind of see what it's actually doing. In fact, let me put it down here so that I can adjust it. And what you see there is the wiper of the pot, and as I turn the pot, you can see the wiper move. The wiper is just like a wiper on a motor, like a brush, I should say, on a motor. Now, this particular potentiometer is a wire-wound pot. But you can see that as I adjust it, the light gets brighter, dimmer. Ooh, ah, ooh, ah. Yeah, okay. Now, this pot you can see is wire wound. You can see the little wire wrapped around it. And you can really see how the wiper just touches the wire. The pots that I've given you are carbon. Potentiometers can be carbon or they can be wire wound. The difference is how much power they can handle, how much current they can handle, basically. Well, here's what's inside the pot. Inside the pot, there is some kind of resistance element, whether it's carbon, like yours are, or wire, like the one I just showed you, something that has resistance on it. And that's 2 of the 3 terminals that are on the potentiometer. Then the wiper, which is the thing that you turn, actually is touching the resistance element as I showed you earlier. That goes to the 3rd lead. Again, it's called the wiper of the pot. The wiper of the potentiometer. And here's how it works. It's really simple. Let's say, for example, that I have a 1K potentiometer, 1,000 ohms. That means that from one side of the resistance to the other side is a 1,000 ohms. If I were to measure the resistor from one side to another, I would get 1,000 ohms of resistance. Depending on where the wiper is set, we can get any value we want. For instance, let's say the wiper's all the way at this side. If I were to measure the resistance with my meter, there's the meter probe. If the wiper was all the way at one side, right now I would have 0 ohms of resistance, because the meter would go through the wiper, right back out again. It never has to hit any of the resistance element at all, does it? It doesn't go through any of that at all. So that would be 0 ohms. Let's say I rotate the wiper 1/4 of the way up. Well, now the current has to flow through the wiper and through part of the resistance, 1/4 of the resistance. Well, shit, if it's a 1K pot and I'm going through 1/4 of the resistance, I guess I probably have about 250 ohms there, which I would. Rotate it halfway up, obviously 500 ohms, because now we have to go through half of the, remember this is resistance here, half of the value of the resistor. You know, if I turn the wiper a little further, 3/4 of the way, 750 ohms obviously. And if the wiper's all the way at the far edge like this, well, now the electric current has to flow through the entire resistance element before coming back out, and we'd have the full scale value of 1K. Now, we're going to look at a bunch of different places that we use pots, and we're going to see, you know, what we use them for as we go through the class. I'll show you more and more things with pots. But how do you test them? Well, when pots go bad, there's only 2 things that generally go wrong with them. First of all, I rarely see bad pots. Usually the only thing that will cause a bad pot is when somebody breaks the damn thing off. You know how sensitive that neck board is. On the neck board of the monitor, there are usually 5 very delicate little potentiometers. In fact, where are those monitor chassis in the back room here? Oh yeah. When you look at a monitor chassis, on the neck board here, this is what we commonly call the neck board of the monitor. For obvious reasons, it goes on the neck of the picture tube. But there are 3 potentiometers here, and these guys are incredibly delicate. These little tiny pots, man, if you just barely hit those wrong, you'll break them right off. There's 2 more over here on the other side right here, and there's a whole row of them back here. There's a whole row of little teeny-weeny pots here. And the problem is that most game technicians are they're used to using big hammers and stuff like that, and you get you get in there with your big old hand, you bust something off. It's real easy to break them off. So that's what usually happens. Yeah, use the big universal backdoor key. Here, let me show you. Universal backdoor key. Oh no, that's this one. Here, this is the one. This is the better one. This is the deluxe universal backdoor key. Anyway, so one thing that happens is you just break them off. The other thing that can happen is the pot can crack like this. Turn in your blue book to page 7, I think it is. The first 10 pages of your book is an article on how to use a digital multimeter. And on page 7, you see checking a potentiometer, testing potentiometers, just so you know where to find it. There's lots of things in the book. I won't necessarily cover everything in the book. I'm not the kind of instructor that will stand in front of you and read from the book. I assume everybody here knows how to read. So I'm just going to show you where to find some things later on in case you forget. Anyway, one of the things that can go wrong with a pot is that the resistance element can crack on these carbon pots. This is especially common where the wiper has been in one place for 7 years. It's a especially common problem on the type of monitor that's in your Vigilante game, Shirley, and that's in this monitor here. There's a potentiometer on these things that it's called black level. It's a brightness control. And it sits in one spot for years and years and years, and eventually it cracks and causes no picture. And then you barely move the pot, and it comes back on full blast. If you ever have a problem where you can't adjust something, you're trying to adjust something, and you just barely move the pot, and the size or the volume or whatever it is that you're adjusting, and the voltage jumps like crazy, the pot's bad. So one of the first things that you do when you test the pot is to check from one end of the from one end of the pot to the other, not the wiper. And what you're doing is you're just checking to see that the pot is continuous. That is, that it's not broken from one side to another. Well, where the hell's that eraser? No. Oh, thank you very much. All right. In other words, what you're doing is putting 1 meter lead on this side, one on this side, checking to see that it's the right number of ohms. Also, there's another cool thing about this. Very often when you look at a little pot, it doesn't tell you how many ohms it is. Sometimes it does, but sometimes you look at a pot and it doesn't tell you. The way you can tell how many ohms a pot is by measuring from here to here and see how many ohms it is. That tells you the total value of the pot. On the other hand, if you checked, let's say it's supposed to be 1K, and you check it with your meter, and your meter says that it's open, then obviously the pot is bad. It's cracked somewhere. So that's test number 1. Then the other thing that can go wrong with a pot is that the connection between the wiper and the resistance element goes bad. It just gets dirty, basically. And you've probably heard this on your car radio or your stereo at home. You go to adjust the volume, it goes... They changed those circuits, and modern radios don't do that anymore for reasons that I can't get into right now. But that's when the pot gets dirty. And typically in a game, what will happen is you'll go to adjust the power supply voltage, and as you just barely move it, the thing jumps up and down, the voltage fluctuates like crazy. Or you're adjusting the vertical size control of a monitor, and it just jumps all around like this. Usually the pot's just bad, and usually all you have to do is just rotate it a few times back and forth, which you don't want to do with the power turned on because you're adjusting something crazy. Turn off the power, adjust it back and forth. Usually that cleans it off. Other than that, they do have some cleaner sprays that you can get at like Radio Shack and places like that. I personally rarely find pots to be bad, and when I do, I usually just change them rather than clean them, to be honest with you. But just to kind of give you an example, we had a service call on a monitor, and the service call was that the picture was jumpy picture. So the service guy went out there, jumpy picture. He pulls the monitor out, brings it back into the shop, and I plug it in on the bench, and it's jumpy, but I realized that it's not jumping up and down like this. It's getting bigger and smaller. The picture's getting bigger, smaller like this. Big difference between this, which would be the vertical size, the vertical position, and this, which is the vertical size, the height of the picture. Well, that's all it must have been. It was just that, and I just took the vertical size pot and rotated it back and forth a few times, Picture was solid as a rock. When I put it back, I didn't put it in the exact same position. I moved it over just a little bit, making the picture just slightly small, which I don't mind seeing a little black on the tops and the sides of the picture personally. And it was fine. That's what he should have done out in the field. That was a really stupid thing to do, because he went out there, saw that it was jumpy, drove 20 miles back to the shop, got another monitor, drove 20 miles back out there to change it. If he had been observant and had noticed the thing, oh, it's getting bigger and smaller. Vertical size, that's all it was just the pot adjustment. Okay, so that's almost all that will ever happen as far as pots are concerned. Like I said, usually I look at them, they're broken in half. A capacitor is basically like a short-term rechargeable battery. It's like a battery that can be quickly charged up and just as quickly discharged. And I can demonstrate that for you here. On this power supply, there's a large capacitor right here on this board. And I can charge this capacitor up by connecting it to this battery. And charge this guy up like this. It's now fully charged. It only takes a fraction of a second to charge the capacitor. Now when I connect the lamp to it, what you'll see is the lamp will glow shortly and then for a short time and then dim out as the capacitor discharges. Here, let me just do it one more time here. Ooh, ah. Charging up, discharging. Capacitor charging up, discharging. And actually, if I don't charge it through the lamp, if I charge it just directly off the battery, that's all it takes. Just a fraction of a second will completely charge the capacitor. So a capacitor is like a very short-term rechargeable battery that can be quickly charged up, but will also just as quickly discharge. Now, if you look at your capacitor, you will see that it is polarized. That is, there's a positive lead and a negative lead. And generally, the negative lead is marked on the side. You'll see like a little minus sign. Sometimes this is an arrow, like that. Okay, can you see it on your little capacitor that you have? I can show it to you. Well, here, I'll show you another one up close here. See, this is the minus side here. If I back up just a little bit here. Get a better look at it. That's the negative side. The positive side is not marked, but there's a negative side. And you'll also notice that the positive lead is the longer of the two. You notice that one lead's longer than the other, and the positive lead is the longer of the two. That's so you can identify. That's so you can identify the capacitor from the bottom of the board. When you have it mounted on a board, you can look at the bottom and see which side's the positive end and negative end. And that's real important because if you connect the capacitor backwards, it will blow up. Not maybe sometimes kind of blows up, not blows up, a little bit. It really blows up. It blows the heck up. Yeah.
Demonstration.
No, not demonstration. Not for now. But it's real important that you connect these properly. I'm always very paranoid when I'm working on with capacitors. Make sure that you get it in there properly, because what's inside these capacitors is a couple of sheets of aluminum foil separated by some brown paper, and the paper soaked in something called electrolyte. Say, Jeff, you got your tools there. Grab a pair of dikes so that I can cut one of these things open. I don't happen to have a pair with me. Danke. I'm going to cut this one open so you can kind of see what's inside. Kids, don't try this at home. In the bottom of this thing is like a rubber plug. Pop. There it is. And here's what's inside. Let me just show it to you up close on the camera here. Smell! If you look inside, here it is all rolled up. Now, let me just take the tape off here. Yeah, it was really important, Mel. You blew it. Okay. And let me just hold this out here so you can kind of see what it looks like. And I can unroll this paper.
Wait a minute, like this?
Well, here, you big babies. Here's the paper, and the what you see here is these two sheets of aluminum foil, and separating them is this paper soaked in something called electrolyte. Electrolyte. The electrolyte is like the, in your car battery, the acid, that's electrolyte. Or in a dry cell battery, if you've ever seen a leaky dry cell, the stuff that's leaking out is electrolyte. Technically, what electrolyte is something that allows something called an ion to migrate. I don't know exactly what I'm talking about even. I don't care, because all I know is that if you hook these things up backwards, they blow up and send little bits of paper and foil all over the place. It just gets all over everything, and this makes a big mess. My high school electronics teacher told me of a guy, they nicknamed him Boomer because he was always putting these things in backwards. So be careful. Now this stuff, this electrolyte, ooh, it really stinks like hell, and it's all over my hands now, and it kind of burns a little bit. And so you should be careful with these things. You're not really supposed to pull them apart. But that's what they look like inside. And as I mentioned before, and as I demonstrated, basically they're like a short-term rechargeable battery. These capacitors are called electrolytic, L-Y-T-I-C, electrolytic capacitors. There are many different kinds of capacitors, but the type that we're mostly concerned with is the type that fails the most. If something never fails, I may never even tell you about it. because I don't care. If it doesn't fail, I don't care what it is or what it does. But the electrolytic capacitors do fail a lot. It's a very common failure, and I'll tell you more about this in just a little bit. And it's especially common in monitors and power supplies. We see a lot of capacitor failures. When a capacitor fails, sorry, let me back up a little bit. Capacitors are rated in microfarads. A capacitor is rated in microfarads. The more microfarads a capacitor has, the more of a charge it will store, the more of a charge it will hold. Now, actually, our unit of capacitance is really the farad, F-A-R-A-D. That's another one of those dead guy terms. In this case, it was named after a guy named Michael Faraday, a brilliant mathematician and electronic genius kind of guy. In fact, it's Michael Faraday that invented the electric motor and discovered electromagnetism and magnetic fields and all kinds of stuff. Really just amazing stuff. And so our unit of capacitance is the farad. Well, a 1 farad capacitor is huge. A 1 farad capacitor, depending on the voltage rating of it, is a gigantic, can be a giant thing. We actually use, and it's much bigger than anything we need in games. We actually use capacitors that are rated in millionths of a farad, microfarads. Now remember before when we were talking about the resistor, the metric prefix, the millions, mega, kilo times thousand, remember that? Well, we use real big things in electronics, and we use real itty-bitty teeny-weeny things as well. So we have mega, which means times 1 million. We have kilo, which means times 1,000. Those are our big things. Then we have itty-bitty things. We have milli things. Milli means divide by 1,000, or times 1/1000th, of course, same thing. And we have micro things. Like, for instance, we can have millivolts, milliamps, milliwatts. And we can have microamps and microvolts and micro things as well. And micro is divide by 1 million, or times 1/1,000,000th of something. And so our capacitors, the electrolytic capacitors that we use in games, the ones that fail a lot, are rated in millionths of a farad, microfarads, millionths of a farad. The one I gave you, I think, is like 100 microfarads, isn't it? If you look at it. Doesn't it say 100?
Yeah.
Okay. Well, we use a capital letter M for mega as an abbreviation. We use a lowercase m for milli. Wow, what are we going to do for micro? Now we're screwed because we only have 2 m's. We only got a capital M and a lowercase m. We have to use something else for million. What we usually do in this case is we go to the Greek alphabet. And we use the Greek letter mu, which looks like this. That's the Greek letter mu for microfarads. And so we abbreviate microfarads like this, mu f, microfarads. And if you look at the capacitor, like for instance this larger capacitor that I have here, oops, 3,300, you see the Greek letter mu, 3,300 microfarads. So you see the term microfarads abbreviated with the Greek letter mu. Anytime you see the mu in front of something, it means micro. For instance, I'll show you later, when we talk about monitors, we'll be talking about things in terms of microseconds. Microseconds. Millionths of a second, the Greek letter mu. But because the Greek letter mu looks a lot like our letter U, you'll sometimes see that as an abbreviation for microfarads. For instance, we might have a capacitor that's 3,300, like I just showed you, microfarads, the Greek letter mu. microfarads. And you'll see it on the schematic diagram and everything. We'll look at those shortly. You know, you might have a capacitor that's 2,000 microfarads. It might be abbreviated UF. Because the Greek letter mu looks so much like our letter U, you might see the term microfarads abbreviated UF. So if you've ever wondered what an UF is a microfarad. Or enough is enough, I guess, whatever. You might also see it abbreviated. You might have a 1,000 MFD microfarad. These things all mean the same thing. They'll be abbreviated all the same way. You could have a capacitor, might just say MF, and that doesn't mean mofo, that means microfarads. And you'll see it on the schematic, but usually the proper technical way is that they abbreviate it with the Greek letter mu, microfarads. The more microfarads a capacitor has, the more of a charge it can store. The more microfarads it has, the bigger, electrically speaking, it is. That is, the more of a charge it will store. For instance, the capacitor that I used to demonstrate that I charged up and then discharged it to show you the lamp deal, this was, I think, 18,000. Yeah, 18,000 microfarads. Typically, in a power supply, we have capacitors that are 3,300 microfarads, like the one I showed you. We use everything from a half a microfarad up to 18, 20,000 microfarads, all kinds of different values, and they do different things in different circuits. One of the ratings, so capacitors actually have two specifications. Electrolytic capacitor, well, all capacitors. One is its capacitance in microfarads. How many microfarads does the capacitor have? Is it 1 microfarad? Is it 10? Is it 4.7? Is it 1,000? Is it 3,300? How many microfarads does it have? The second rating of a capacitor is the voltage rating of the capacitor. The second rating is the voltage rating of a capacitor. What's the voltage rating on the cap that you have? It's 100 microfarads, 10 volts, isn't it? Okay, what the voltage rating means is the voltage rating of a capacitor is the maximum amount of voltage that the capacitor can handle. The voltage rating of a capacitor is not how much voltage it puts out. It only puts out what you put into it. The voltage rating of a capacitor is the maximum that capacitor can handle. For instance, if I take a 16-volt capacitor and charge it with a 6-volt battery, I only get 6 volts out of it. It's the maximum it can handle. You have to substitute parts a lot. When you have to substitute capacitors, you can always use a capacitor with a higher voltage rating. I do this a lot. For instance, I carry around these boxes here, and they're basically just like tackle boxes full of capacitors. It's just full of different kinds of capacitors. One common value that I use a lot is 10 microfarads. And in here I've got 10 microfarad, 200 volt capacitors. But a couple of weeks ago I had to fix a monitor in one of the classes, and I needed a 10 microfarad, 16 volt capacitor. I used the 10 microfarad 200 volt. It works fine. Remember, it's the voltage rating of a cap isn't how much it puts out. It's not going to put out 200 volts. It's the maximum it can handle. So it's kind of just like in your automobile. Let's say you have a little Toyota or something, and your car battery is only this big. You could put a car battery in that's this big. You just won't be using all the capability of it. Same kind of thing. Okay? So you can always go up in voltage. In many cases, you can go up in microfarads as well, but you have to be careful about that. And at this point, you folks are not advanced enough to know what I'm talking about in terms of when you can do it. I'll show you later on, though. Primarily, for now, let's leave it at this. You can always use a capacitor with the same or higher voltage, but the number of microfarads should be the same when you change capacitors. For now, I will tell you places where you can actually get away with more capacitance, and it works perfectly okay. But capacitors fail. Electrolytic capacitors fail a lot. It's a pretty common failure. In fact, where parts like diodes and transistors and resistors can theoretically, they can kind of last forever. A capacitor, an electrolytic capacitor, is guaranteed to fail eventually. 100% of the time, electrolytic capacitors eventually fail. And the reason for that is that the electrolyte, the stuff that's... What did I do with that torn apart capacitor?
I think you tossed it.
Did I toss it somewhere? Well, that electrolyte that I showed you, here it is. You know, that soaks the paper, and you can kind of see that it's wet. You can kind of see through it. The electrolyte eventually dries out. That's what happens. And heat is the thing that causes that to happen. Heat is the number one enemy of these things. They don't like to run hot at all. And you know that, especially in a monitor, it gets quite hot up there. Not only is it at the top of the game where all the heat rises, but the monitor itself generates heat. The picture tube gets hot, and some other stuff, a lot of resistors and things get hot in it. And as a result, electrolytic capacitors fail a lot. And when they fail, what happens is they become less of a capacitor. Let's say it starts out as 3,300 microfarads. Over a period of time, it loses its charge, loses its ability to hold a charge. It becomes a 3,000 microfarad. And then a couple of months later, it's only 2,500 microfarads. And then it becomes a 2,000 microfarad. You know, it just becomes less of a capacitor. Now, depending on what the circuit is that it's in, you'll see all kinds of different symptoms. In a monitor, it causes everything from a distorted picture, where you've probably seen this, where the picture is shrunken down at the top, squished at the top, and stretched at the bottom, or the sides of the picture are curvy, it just looks distorted. Those are capacitor failures. In a power supply, we'll see that there's lots of capacitor failures in power supplies, and it causes everything from a power supply that just doesn't work at all to a power supply that creates all kinds of strange electrical noise. Sometimes you've seen this on the screen where you see the video game playing, whatever the game is, and you see these diagonal lines, very closely spaced, kind of drifting all around the screen. It's called herringbone interference. That comes from the bad capacitors in the power supply. We'll talk more about that on Wednesday. Now, fortunately for us, much of the time you can look at a capacitor and see if it's good or bad, which is really excellent. Much of the time you can just look at it and see if it's good or bad. And here's the kind of thing you're looking for. Number one, whoa, hey, avalanche. When you look at the capacitor, if you look at the top of it, do you see how the plastic coating is even all the way around the top? If you look at this plastic coating, this edge here, do you see how it evenly covers the top? If this is shrunk back, if this is pulled back at all, that capacitor is on its way out. What did I do with my bad caps? Here they are. You notice a couple of things about this cap. Number one, the plastic coating, you see how it's pulled back somewhat. It gets much worse than this, actually. I'm trying to get the reflections down here. If you see that, well, basically, if you see that the plastic coating, instead of coating the top like this, has pulled down like this, and you see the metal part, the whole disc on the top exposed, that's definitely bad. There's no question about that. Another thing you'll see is that the top will be domed. That is, the top is supposed to be perfectly flat. And if it's pooched out at all, it'll swell up. You can just barely see here that it's not exactly perfectly flat. You see how it's kind of domed a little bit, not terribly. But if it's like domed at all on the top, like a bad can of pork and beans, that's definitely bad.
Oh, man.
And then when it gets really bad, you see this. You see that the top is blown right open, and you talk about being domed. That's what I'm talking about right there. Now in this case, it's broken open. This is the safety vent. On the top of most capacitors these days, you'll see that the top is scored. And the reason that the top is scored is that's a safety vent, so that and here you can see that see how the top is scored on this one. It's a safety vent so that when the capacitor does go bad, it just opens up and lets the pressure out. Instead of having this top sail off and become a missile, which is what happens, the safety vent just opens up and lets the pressure out. We have a hole in the door of our shop that's about the size of a dime. From you talking about, let's blow one up. Well, that's exactly what happened in the shop, and the guy said, hey, I'm going to blow one up, and he put it over here, hooked it up backwards, and it shot, it was a good 10 feet over to the door, and just blasted a hole in it. So be careful, like your mom said, you can put your eye out with that thing. You got to really be careful with capacitors. It's entirely possible if you put them in backwards that they'll blow up.
How big was that door?
Well, it was just a hollow core door. Granted, it was like, hey, can you close that back door for me, please? So, it wasn't the thickest door in the world, but certainly if it hit you in the face or the eye, it would really, really hurt, to say the least. Now, capacitors. If a capacitor looks bad, and again, the three criteria is the top domed, is it curved at all on the top? Bad. It should be perfectly flat. Is the plastic coating on the top shrunk down at all? Bad. Or is that vent busted open? Obviously, that's bad. Then you definitely have to replace it, but sometimes capacitors look good when they really are bad. And unfortunately, you cannot use your digital multimeter to check capacitors. You have to have a capacitor meter. You have to have a special meter just for capacitors. Which is really a shame because a capacitor meter can cost you 60, 70, 80 bucks. I paid 150 for this one, but you can get them cheaper than that. And yet it only checks one thing, capacitors. And your meter, which only costs 40 bucks, or can only cost 40 bucks, checks everything else, which is really bizarre. But using the capacitor meters is really pretty simple. All you do is set the capacitor meter for whatever range you want, just like with the resistors. For instance, there's 2 microfarads, 20 microfarads, 200 microfarads, and so on. And all you have to do is jam the capacitor into the meter. For instance, it has these clips too, or you can just put it in here like this, making sure that you get the polarity right. I turn on the meter. Meter says that this is 110 microfarads. It's supposed to be 100 microfarads. It's 110. This capacitor is good. When capacitors fail, the number of microfarads is less. In other words, it's supposed to be, well, for instance, there's a common problem in a Hytron power supply. There's a 220 microfarad capacitor. Fails all the time. It just fails. And I'll point that out to you later on. And you pull that out and you put it on the meter and it says it's only 27 microfarads and it's supposed to be 220 or it's 100 microfarads or something. If it shows you even 10% less than what it should be, it's definitely bad or it's on its way out, one or the other. Because here's a new 100 microfarad. You can see it says 109, 110. It's 10% over. Usually, almost all electrolytic capacitors, when they're new, are about 10% over what they should be. That's good. That's good because remember, when capacitors fail, they lose their ability, they lose their capacitance. So when I see one that's even at all lower than whatever's printed on the cap, I got to say, well, this thing's on its way out. Capacitors are usually not a catastrophic failure. Capacitors usually fail a little at a time. They start to get worse and worse and worse. And in a monitor, you see increasing amounts of distortion on the screen. In a power supply, for instance, in this one power supply, the Hytron style that I was mentioning before, it does the weirdest thing. You turn on the game and it doesn't come on right away. And then 5 minutes later, bing, it fires up by itself. And the first time I ever got this call, I went, you're wrong. I mean, the call was, yeah, the machine takes 5 minutes to warm up. Well, there ain't nothing in a game that takes 5 minutes to warm up normally. I'm going, no, you must be wrong. Really, man? No, really? Well, okay, I'll be right out there. And I go out there in the liquor store, and they got it unplaced. Plug it in. They say, you wait. Okay, it's like an Airborne liquor store. You wait. Okay, fine. So, have a Coke. Okay, fine, have a Coke. Sure enough, it doesn't come on. I'm going, well, let me just fix it. No, you wait, you see. Okay. Yeah, 5 minutes later, boing, the thing fires right up. Bad capacitor. Capacitors are funny like that. Sometimes when they're cold, they won't work, but as they warm up, the problems go away. You see this on monitors a lot. When you first plug it in, it looks like crap. And then after it heats up, the sides straighten out a little bit, and it gets bright, and it looks okay. Those are typical capacitor failures. As we'll discuss later on in a monitor, very often when you change, if you have bad caps, you want to change them all at once. And I'll give you a source for these capacitor kits. where you can replace them all for a pretty reasonable price. In fact, by virtue of coming to the class, you get a 15% discount. So I'll tell you about that a little later on. Now, I want to show you one thing about checking capacitors with a digital multimeter. And the only reason I'm showing you this is to tell you not to do it. What'll happen is you'll go back and you'll be talking to some kind of a hotshot and you'll say, Randy's full of shit. You can check capacitors with your meter. Watch. Here's how you do it. Well, this is what they're talking about. And I just want to show you this to tell you not to do it. Here's what I mean. They'll put the meter on some kind of an ohm scale. They'll put it like on, they'll put the meter on like the 2K scale or something like that, and depending on the size of the capacitor, and put their meter leads across the cap, positive to positive, negative to negative, and watch the meter charge up. Oops, that's a little fast here. Let me go to a different range. They'll watch the capacitor charge up on the meter. 1, 2, 3.1, 3.3, 0.4, 6, 7, 8, 9, 4.6, 5. You can see that it's charging up. And I mean, the meter's changing. You can see it's increasing in numbers. Well, obviously, this capacitor is taking a charge. That's what they say. Well, it's taking a charge. It's good. Well, in a way, they are correct. Yes, it is definitely taking a charge. But unless you have another one of the same capacitor and a stopwatch so that you can tell how long it takes it to charge up, you don't know if it's the correct value. In other words, a 100 microfarad capacitor will charge up just like a 1,000 microfarad will. It just charges faster. So you need to be able to tell exactly how many microfarads it is. And so I strongly suggest that if you're going to do a lot of monitor repair, you get a capacitor meter. Now, you don't have to have one. In fact, I've only had one for the past few years, really, and I've repaired lots of monitors before I had a capacitor meter. But the only other way to check it out is by substitution. That is, if you have a shitload of capacitors in your shop and you think that capacitor is bad, pull it out, try sticking a new cap in. If the problem goes away, obviously that cap was bad. And that's the way I've been doing it for years, but it's a real hassle unless you have a lot of capacitors. Because you say, I think that one's bad, you go drive over to the store, you pick up a capacitor, you come back and you stick it in, and shit, that's not it, you go get another one, and it's a hassle. For $80 or whatever it's going to cost you for a capacitor meter, if you're doing a lot of monitor repair, especially because that's where we have a lot of cap failures, it's not a bad idea to have a capacitor meter. Quite frankly, though, when I have bad capacitors in a monitor, and again, we're going to discuss this in great detail on Thursday, I usually end up changing just about all of them anyway, on the theory that when one's going bad, they're all probably going bad because they're all the same age. We might as well get rid of them all. And so, if you're a small operator, I definitely don't suggest you run out and buy a capacitor meter, as long as you have a source of capacitors. But capacitors, you do need to get a lot of them. We'll be talking about part sources later on. In your book, there's a whole list of places where you can get parts for a pretty reasonable price, and we'll talk more about those as we go through that. Okay, but that's capacitors. And again, they fail a lot, especially in monitors. We have a lot of cap failures in monitors.
Hi, welcome to the Arcade School. You know, today's video games and electronic pinball machines are really state-of-the-art computer sophistication. And quite frankly, that's left a lot of mechanics a little bewildered. How do you fix something when you can't see the stepper step? How do you fix something when you can't see the relays open and close? Well, in fact, in a way you can see the stepper step, and in a way you can see the relays open and close. But you can't use your eyes. You have to use a piece of test equipment. And the piece of test equipment you want to use is called a digital multimeter. This particular digital multimeter is made by a company called Beckman. It's the Beckman Tech 310. And like other digital multimeters, this particular meter can be used to measure AC and DC voltage, AC and DC current, and resistance. There's also a very special range on this meter. It's called the diode test range. By using the diode test range, which is built right into the meter, we can test diodes and transistors without having to buy a separate piece of test equipment to do it. During this lesson, we'll be taking a look at the digital multimeter and effective ways to use it to repair electronic games. Let's take a closer look at this extremely versatile piece of test equipment. The single selector knob in the center of the meter selects not only the function of the meter, that is, voltage, current, or resistance measurements, but also sets the maximum range for each individual setting. DC voltages as high as 1500 volts and AC voltages as high as 1000 volts can be measured with the meter. The meter can also measure resistances from as little as 1/10 of an ohm up to 20 million ohms. Although the meter has AC and DC current measurement capabilities, we don't measure current when repairing games, so we won't talk about the current settings. The meter also includes a special diode check function that's useful for checking all types of different semiconductors. We'll look at all these tests during this lesson. Well, one of the easiest tests that we can make with the meter is to measure the voltage of a battery. We use batteries all over the place in electronic games. For instance, this Williams video game uses a battery as a backup to maintain the bookkeeping information and the high score to date and that other important information that we don't want to lose when the game's turned off at night. So let's take a look at the voltage tests and see how we measure voltage using the digital multimeter. Start the test by inserting the black meter lead in the jack marked COM for common. Our black lead will always be placed in the common jack. On the left is a jack mark for volts and ohms. That's where we'll put our red meter lead. The next thing we have to do is set the meter to read DC volts. And here we've set it to the 2-volt range because the battery's voltage is only around 1.5 volts. There are 3 batteries in this Williams video game that maintain the bookkeeping information. And they're installed in these battery holders right down here on the computer board. And they just slide in pretty easily, just like this. To measure the voltage of the battery, we'll take the red meter lead and touch it to the positive terminal of the battery, and the black meter lead to the negative terminal of the battery. We can read the voltage right off the meter, approximately 1.3 volts. Of course, you won't be measuring the voltage of a battery nearly as often as you'll be measuring the 5-volt power supply in the game. That 5-volt power supply is really important. All of the computers in all of the games you work on require an exactly regulated 5-volt power supply to operate. In fact, it can only vary maybe, a quarter of a volt either way. If the voltage drops down below 4.75 volts, or if it goes above 5.25 volts, the computer may malfunction. In fact, it may not work at all. There are other voltages as well. For instance, in the Defender game, there's a positive 12-volt power supply and even a minus 5-volt supply. That's right. We can have negative power supplies in a game just as often as we can see positive power supplies. Both supplies work approximately the same way. The only difference is that in a negative power supply, the flow of current is reversed. We'll measure both those power supplies, positive and negative, the same way with our meter. To make it easier for you to test the power supplies in a game, many manufacturers are now installing test points right on their printed circuit boards. Well, this makes your job real simple. For instance, here on this Tempest printed circuit board by Atari, there's a test point marked GND for ground, and we'll connect our black meter lead to this test point. There's also a 5-volt test point on the printed circuit board, and it's right here, right next to this red LED that is glowing to indicate that we do have the 5 volts to the printed circuit board. With the meter set to the 20-volt range and the red and black leads in place, we can see the meter reads exactly 5 volts. All games require a 5-volt power supply to operate, and a pinball machine is no different. In this pinball machine, the 5-volt test point is seen here. It's labeled test point 5 right on the printed circuit board. And with the red lead on the test point, we can read the voltage right off the meter, 5 volts. Don't forget to put your black lead on ground, like the ground braid or the special ground test point. Well, even if your game doesn't have 5-volt test points or ground test points, there's still a real easy way that you can check the 5 volts going to the computer board. Do you see how all the integrated circuits on the board are arranged in rows? And do you see how there's this heavy printed circuit board trace running up and down each side of the rows of chips? Well, one of these traces, or power rails as they're called, carries the 5 volts to all the ICs, and one carries the ground. By placing the meter leads across the power rails, we can read the voltage directly across it. And here we see that it's real close to 5 volts. It doesn't matter which lead you put where. If you accidentally reverse the meter leads, the meter will simply show a negative voltage. So you see, with the digital multimeter, you don't have to worry about accidentally reversing the leads. We can measure the voltage of alternating current just as easily as we can measure the voltage of a direct current source like a battery or a power supply. But instead of setting our meter to read DC volts, we'll set it to read AC volts. Say, for instance, we wanted to measure the voltage from a floor receptacle. Well, we know that that voltage is somewhere around 120 volts AC, so we'll set our meter to the 200 volt AC range. With the meter set on 200 volts and the red and black leads inserted into the AC receptacle here, we can measure the voltage and read it right off of the meter. In this case, it shows 117 volts. If I were to accidentally set the meter too low, say on the 20 volt range, the meter reads OL. Well, OL stands for overload, but that doesn't mean that I'm hurting the meter in any way at all. It simply means that the input voltage coming into the meter through the red and black leads here is higher than the setting here on the selector knob. In fact, I can actually rotate the selector knob through all of the ranges, including the resistance range, without fear of damaging the meter. The meter is fully protected or idiot-proofed against all kinds of accidental high voltage overloads. Well, if this were a conventional analog or needle type of meter, you'd see little wisps of smoke coming out of the back of the meter, and you could watch the needle peg to the right as the meter instantly destroyed itself. In this case, we don't have to worry about it because of that overload protection circuit that's built right into the meter. Now that we know how to measure DC voltage and AC voltage as well, let's take a look at another very important test that we can make with our meter. There are certain types of power supply failures that allow a small amount of alternating current to ride on top of the direct current. This condition is known as power supply hum or power supply ripple, and can generally be attributed to a bad filter capacitor. The filter capacitor is very important for a power supply because it assures that the power supply voltage remains absolutely pure and constant. When the power supply has excessive ripple in it, the computer may malfunction or it may not work at all. So let's take a look at what we'll see when we have a bad filter capacitor in a power supply. As long as the 5-volt supply remains constant, the computer works normally and displays the picture you see here. But if the capacitor fails, hum bars occur. These horizontal blue bars are known as hum bars and are a visual indication of a bad filter capacitor. When the capacitor fails, the power supply does not remain constant. That is, the voltage is constantly changing. When we measure the DC voltage of the power supply with our meter set on the 20 volt range, the supply reads 4.58 volts. That's because the meter averages the times when the voltage is up at 5 volts with the times that the voltage is allowed to drop lower due to the bad filter capacitor. Well, we can easily determine if this problem is low voltage or ripple by switching our meter to read AC volts. When we switch the meter to read AC volts and check the voltage again, we see that the meter reads 0.6 of a volt of AC ripple riding on top of the DC. It doesn't matter if the power supply is in a video game or a pinball machine like this. Ripple will still test the same way. When the voltage reads too low on your meter, switch your meter to read AC volts and look for that AC ripple. In this case, 1.6 volts of AC ripple riding on top of the 5 volt supply means that we have a ripple problem here, usually caused by a bad capacitor. In this case, though, we can trace the problem to a broken wire. The broken wire disconnects the capacitor and allows excessive ripple into the supply. This video connector carries the video signal from the computer, and we can check with our meter and see if this video signal is present by inserting the meter lead into the connector. The changing voltage that we read on the meter indicates that the video is present. The higher the voltage, the more of that particular color is appearing at that time on the front of the screen. In this case, we definitely have video.
Steve Dacus for Wicco. You've heard the old saying, time is money. That statement was true nearly 200 years ago when Ben Franklin first said it, and it's still true today, particularly in our business. This kind of thing costs you money. At Wicco, we've been in business over 40 years, creating the fastest, most efficient, up-to-the-minute means of giving you the good service and the products that you need. We have 5 distribution centers throughout the nation with everything that you'll need under one roof. And we have a pretty simple way of putting them under your roof. Our new catalog comes complete with diagrams, descriptions, and prices on everything that we sell. In the front cover, there's complete instructions on how to purchase, how to receive personal attention, and at the top is our Wicco guarantee of satisfaction on every item that we sell. At Wicco, we'd like you to become as familiar with our catalog as you are with our name. Chasing down the parts that you need can cost you your most valuable commodity, time. At Wicco, we believe we can save you time and money. We're Wicco, world's largest distributor of parts and supplies to the amusement, music, and vending industries.
The resistance setting of the meter can be used to check resistors like this. This is a 2 ohm resistor, so we'll set the meter on the 200 ohm scale. In this case, we can read resistances from as little as 1/10 of an ohm up to 200 ohms. When we place the leads across the resistor, we read 1.9 ohms, which is within the tolerance of the resistor. This is a 47 ohm resistor. Again, we can tell by the color code that it's 47 ohms. And when we place our meter leads across it, it reads 49.5 ohms. Because of the tolerance of the resistor, this is again within its limits. This is a 47,000 or 47K resistor. We can't use the 200 ohm scale to measure it, so we have to go up to the 200,000 or 200K scale. When we place our meter leads across this resistor, it reads 44.3, but it's not 44.3 ohms because the setting is on the K scale. This is actually 44.3 thousand ohms, or 44,300. This is a variable resistor, or potentiometer. This is a 25,000 ohm potentiometer. So we'll start our test by measuring between the 2 outside terminals and using the 200K scale of the meter. The meter shows 25,000 ohms. The second part of this test is to check between the center wiper connection and either side. We can now see the resistance change from a minimum of 0 ohms all the way up to the full scale value of 25,000 ohms as we rotate the wiper. A bad potentiometer will test OL between the 2 outside terminals or will jump wildly as the potentiometer shaft is rotated. This is a good potentiometer. Pinball coils have a low resistance, so we'll test them on the 200 ohm scale. Speakers can also be tested by using the meter. Speakers should read between 4 and 16 ohms. So we'll use the 200 ohm scale to check the resistance right here. With the meter set on 200, we read approximately 8 ohms, 7.6. Fuses are also tested with the meter on the 200 ohm scale. But be very sure that when you place your meter leads across the fuse, you touch the fuse holder and not measure across the two end caps of the fuse. If the connection is bad between the fuse and the fuse holder, you won't know it unless you measure it this way. Also, it's important that you never simply look at a fuse to determine if it's good or bad. This fuse looks perfectly good. You see the fuse element inside looks complete. And yet, when we test it with our meter, the meter shows OL. Of course, that means that the fuse is open. It's a blown fuse. What we should see is this reading, just as you see here. So this fuse is open. It's no good. As with the fuse test, we test switches on the 200 ohm scale. When we depress the switch, we see a short circuit. When we let go of the switch, we see OL. This is a good switch. Diodes are semiconductors that act as one-way gates for current flow, and there's a special diode test range right here on the meter. The readings we should get for a diode are some reading in one direction and OL in the other. Normally, you will read between 0.5 and 0.9 in one direction and OL when the leads are reversed. Occasionally, you may see some very large diodes like this one that will read slightly below 0.5. As long as we get an OL reading when the leads are reversed, the diode is good. Bad diodes look the same as good diodes. The only way to tell is with your meter. This one reads OL in one direction and OL when the leads are reversed, so this diode is open. But the most common diode failure that you'll see is a shorted diode like this. Transistors are also tested with the meter set to the diode test range. This is the base of the transistor, this is the emitter, and the case is the collector of the TO3 package. We'll start our test by putting the red meter lead on the base of the transistor. With the red lead on the base and the black lead on the emitter, we'll read a junction drop of between 0.5 and 0.9. Leaving the red lead on the base and touching the collector, we should see the same reading. Then we'll reverse the leads and place the black lead on the base. Again, we'll check from base to emitter. This time we should read OL. When we move the red lead to the collector, we should also read OL. Well, many people feel that this is a complete transistor test, but it's not. There's one very important test that you have to make before proclaiming that transistor to be good. Emitter to collector should read OL, and it should read OL in both directions, no matter which way you put your meter leads. This is a bad transistor with a typical failure. Base to emitter reads junction drop, base to collector as well. When we reverse the leads and put the black lead on the base to emitter, OL, and base to collector, OL. So far, so good. But when we make that final test from collector to emitter, look, the transistor is shorted, and it's shorted in both directions. Integrated circuits that belong to the TTL family are used quite often in games. When these ICs fail, very often their inputs or outputs will short out, and we can pick up this short with our meter set to the diode test range. This is the only test where we will ground the red meter lead and use our black meter lead to probe each of the pins. A good input or output should read a junction drop like this. But a bad input or output will usually show considerably lower reading like this. And finally, let's take a look at one more test. If the printed circuit board is shorted, you can't find the short circuit with your meter set to resistance. Look, no matter where we test the board, when we measure resistance across the power rails, the board appears shorted. It appears shorted everywhere because all the rails are tied together. The short will often be caused by one of these small capacitors which are wired directly across the power rails. They look like diodes, but they're capacitors. We can't find it with our meter set on resistance, But we can find the short if we move our meter selector to read voltage on the lowest DC range. Connect a battery to the power rails. Connect the ground lead to the ground test point and the red lead, which is connected to the positive terminal, to the 5-volt test point on the printed circuit board. What we're trying to do here is power the shorted board with the battery. Then take the meter and connect the meter leads to each individual power rail one at a time. As we get closer to the short circuit, we should see the voltage drop. Here it's 83. Here the reading is 55. Here it's 21. But here the voltage has gone up, so we've passed the problem. The short must be in this power rail here. Now we can move up and down the power rail to find the shorts. As I move in this direction, the voltage increases, so I'm going the wrong way. When I move the leads down toward the bottom of the board, the voltage decreases as I get closer and closer to the short circuit. If I pass the short circuit, the voltage will go up. And right here we see the voltage has started to rise, so I'm going to back up and move my leads back the other direction. By moving the leads back and forth like this, I can get down to the exact point where I find the short circuit. The lowest voltage will be the position of the shorted component. In this case, it's this capacitor. Well, that's it as far as our digital multimeter tests are concerned. And you can see that the digital multimeter is an extremely effective piece of test equipment, and you won't want to go anywhere without it. But that's all the time we have for now. So I'll see you next time at the Arcade School. Bye-bye.